my dear students? I hope you all are doing great. Students, once again, I welcome you all on this amazing platform of PhysicsWallah English channel. Student, if I talk about today's lecture, it's one of the most important lecture of entire chemistry. You can say this particular lecture, this particular topic which we are going to discuss today, it's the backbone of chemistry, whether it's inorganic chemistry, whether it's organic chemistry. If this chapter is not crystal clear, you cannot understand chemistry, right? So the topic which we are going to discuss today is chemical bonding, right? A much awaited chapter. So student, without wasting any further time, let's start our today's session. And it's a natural tendency of each and every atomic and subatomic particle of the universe to attain stability, right? Students, now whenever we are in the free state, we are more disordered, right? We are having more energy. In terms of potential energy, our potential energy is relatively more. But whenever we are in the combined state, whenever we are in the bonded state, our disorderedness, our natural randomness decreases, right? So student, and everyone wants to attain stability. And how will they gain stability? By decreasing their randomness, by decreasing their potential energy. Students, in order to decrease their potential energy, in order to decrease their randomness, in order to decrease their entropy, they form bond with the other one, right? And during this their bond formation, they lose energy and gain stability. Student, can I say any bond, whether it's physical bond, chemical bond, any bond, energy is released in the process. So can I say bonding is a exothermic process, student. Students, now since it's a chemistry lecture, it's time to focus on chemical bonding aspect. How do we define it? Basically, it's a chemical force which acts between two or more than two atoms to hold them together as a stable molecule. A force that acts between two or more than two atoms to hold them together as a stable molecule. Initially, when these atoms are in non-bonded state, they are much more disordered, they are much more free, they are having higher potential energy. As soon as they become in the bonded state, as soon as they are in the bonded state, they lose energy. They have gained stability. So student, bond formation is always a exothermic process. During the bond formation, energy of the system always decreases. Now let's try to understand the cause of this chemical combination, the cause of chemical bonding. Student, for each and every phenomenon which is occurring on this earth, the driving force is stability. So the cause for this chemical combination is also stability. Now let's see how do the two atoms combine. And we'll try to understand this phenomenon with this diagram. Let's suppose I'm having two atoms, A and atom B. This is the nucleus of atom A, nucleus of atom B. Let's suppose the initial separation between these two atoms, the distance of separation between the two atoms is infinite initially at t equals to 0. When the separation distance is infinite, can I say the potential energy of the system will be 0? Here, the separation distance between these two atoms is infinite. The potential energy of the system is 0. Now, if they try to approach towards each other, can I say attractive force will start operating? Attractive force. And can I say this attractive force is mainly between the nucleus of one atom and the electrons of other atom. Nucleus of atom A, electronic clouds of atom B. Nucleus of atom B and electronic clouds of atom A. The force between a positive charged particle is always a attractive force. Student, if the attractive force is dominant, then what will happen? Stability will increase, means potential energy of the system will decrease. So as the atoms are approaching towards each other, means attractive force is much more dominant, then only they will try to approach towards each other. and if they are approaching towards each other, the potential energy of the system is decreasing, means energy is getting released. Right, student? Now we can see in the diagram this particular energy level is corresponding to minimum potential energy level. Basically, at this separation distance, my potential energy is minimum. So basically, at this much separation distance, the bond formation between the two atoms A and B has occurred. At this separation distance, the bond formation between the two atoms A and B has occurred. So basically, at this energy, A and B are in the bonded state. So this particular energy is corresponding to bond energy. Bond energy. Am I clear, students? The minimum potential energy where this bond formation has occurred corresponds to bond energy. And the strength of any chemical bond simply depends on bond energy. Am I clear? The more is the energy released, better will be the strength of a chemical bond. Am I clear, student? And this particular separational distance corresponds to bond length. Bond length. Am I clear? This particular distance, with this particular separational distance, I can say it as bond length. If the atom further try to approach towards each other, now students, repulsive force will dominate. Why? Because we will have internuclear repulsion. The repulsive force between the nucleus of two atoms. At the same time, we will have repulsive force between the electron clouds of the two atoms. So if the atoms further try to approach towards each other, the repulsive force will dominate and potential energy will suddenly shoot up. Am I clear, students? I hope you understood this phenomenon of chemical bonding. Now, students, let's first of all discuss the different types of bonding. We have understood bonding is always a exothermic process. Now, on the basis of this bond energy, we classify bonding in different categories. Let's try to understand. Student, on the basis of this bond energy, on the basis of amount of energy released during a bond formation, we have two types of bonding. One, bonding is of two types. One, chemical bonding, and the other one is physical bonding. In case of physical bonding, the molecules are not bonded chemically. Simply an attractive force is dominant. They are very close to each other, but they are not bonded physically, or they are not bonded chemically. Am I clear? Whereas in case of chemical bonding, the two atoms are chemically bonded. Am I clear, students? So obviously this physical bonding is relatively a weaker bonding. Here the bond energy is relatively very less. The amount of energy released during this physical bonding formation is relatively very less, where the amount of energy released in chemical bond formation is relatively much more higher. Am I clear, students? I hope these things are crystal clear. In case of chemical bonding, if chemical bonding phenomenon has occurred, more than 42 kilojoules per mole energy is released. Whereas in case of physical bonding, if I talk about this Vander Wall bonding, almost 10 to 12 kilojoule per mole energy is released. Somewhat more amount of energy is released in case of hydrogen bonding. These two are the examples of physical bonding. Remaining all are the types of chemical bonding. Student, so if I talk about this chemical bonding, we have ionic bonding. Basically, such types of bond is formed between a electropositive and a electronegative elements. So between metal and non-metal. Am I clear? Covalent bonding formed between two electronegative elements. So it's simply the bond formed between the two non-metals. In an easier word, electronegative plus electronegative means non-metal plus non-metal. The bond formed between the two non-metals. It's covalent bonding. coordinate bonding is also a sort of covalent bonding itself. So mainly it's also formed between a non-metal and a non-metal. The next one, metallic bond. Such bonds are formed between two electropositive elements. Metallic bond is the bond formed between two metals. We'll talk about each and every bond. Metal plus metal. And in case of this physical bonding, we have two types of bonding, Vander Wall bonding and hydrogen bonding. We'll discuss about these bonding also separately in this particular lecture only. Now let's try to understand this covalent bonding. First, such type of bonding is formed between two electronegative elements. Bond formed between two electronegative plus electronegative means the bond formed between two non-metal. Such type of bonds are covalent bond. How it is formed? It's simply formed by the sharing of electrons, by the sharing of unpaired electrons between two atoms. Okay. It is formed by the equal contribution or sharing of unpaired electrons present in the valence shell of two atoms. Student, when they share electrons with two atoms, basically they attain its nearest noble gas configuration. They attain either its duet or they attain its octet. By attaining octet, they gain stability. Let's try to understand it. If I talk about this hydrogen, single electronic species, one electron, one more hydrogen atom, one electron, right? Now, if these two hydrogen atoms will share one electron, can I say this hydrogen atom will have two electrons? So it's basically attaining the configuration of helium. Similarly, this hydrogen will also have two electrons now. So it will also attain the configuration of helium, and by doing so, they will attain stability. Same is the situation with oxygen atoms. Oxygen atomic number Z equals to 8. Configuration 1s2, 2s2, 2p4. 6 valence shell electron, 2, 2 and 2. One more oxygen atom, 2, 2, 2. Now, if each oxygen atom will share two electrons, this particular oxygen atom will have its octet getting complete, and this particular oxygen atom will also have its octet getting complete, right? This one will attain the configuration of neon. It will also attain the configuration of neon, right, students? So once again, the driving force for this covalent bonding is also stability only. Am I clear? Here, the bond is formed between the sharing of by the sharing of electrons between two electronegative elements. When the two electronegative elements share their valence shell electrons, basically the bond is formed, and the bond formed is covalent bond. Okay, let's move ahead. Student, now let's try to understand what do we mean by the term covalency. Covalency, first of all, in a simpler word, can be defined as the number of covalent bond formed between two atoms. Let's suppose I am having A and B. If one covalent bond is formed between A and B, the covalency is 1. The number of covalent bonds formed by an atom in a covalent molecule, it's nothing but covalency. In other words, it can be defined as the number of unpaired electrons present in the valence shell either in the ground state or in the excited state. This definition is really important. The total number of unpaired electrons either present in the ground state or in the excited state is nothing but covalency of an atom. Covalency is simply defined as the total number of unpaired electron either in the ground state or in the excited state. Let's try to understand this covalency with few examples. Let's first of all talk about carbon. What is atomic number? 6. Configuration 1s2, 2s2, 2p2, right? It's the ground state configuration, 1s2, and this is the valence electrons, right? 2s2 and 2p2. This is the ground state configuration. So in the ground state, how many unpaired electrons are there? 2. So in the ground state, what is the covalency of carbon? 2. Covalency is 2. We can see here in CF2 molecule, CF2 radical, right? Here, how many covalent bond is formed? 2. Am I clear? CO, the number of covalent bond formed is 2. So in the ground state, what is the covalency of carbon? The covalency of carbon is 2. It can form 2 covalent bonds. It's having 2 unpaired electrons. Now, in the excited state, what will happen? What will happen? This particular electron will jump to this orbital. Now, how many unpaired electrons will have? 1, 2, 3, 4. So student, in the first excited state, I will have 4 unpaired electrons. So what will be the covalency of carbon in the excited state? The covalency of carbon in excited state will be 4. Means in the excited state, carbon can form 4 bonds. As we can see, in maximum cases, carbon is a tetravalent atom. It's mainly forming 4 covalent bonds. CH4, 4 covalent bonds. CO2, 4 covalent bond. Am I clear, student? I hope these things are clear. Students, now let's talk about covalency of few more second period element. If I talk about a second period element, do they have any d orbital? No, 2d does not exist, right? And one more important point. Student, whenever we do excitation, only internal excitation is allowed. What do we mean by the term internal excitation? Means in the excitation process, the principal quantum number, the energy cell, should not change. Am I clear? Means I cannot jump from second energy cell to third energy cell or third energy cell to fourth energy cell. The principal quantum number value should not change. Only internal excitation is allowed. External excitation is not allowed in case of covalency. While defining covalency, external excitation is not allowed, right? Okay. Now, if I talk about this nitrogen, Z equals to 7. So what's the electronic configuration? 1s2, 2s2 and 2p3. Valence cell 2s2 and 2p3, right? Okay. In the valence cell, if I look at this particular configuration, how many unpaired electrons? 3 unpaired electrons. So in the ground state, what is the covalency? 3. Now, if I do excitation, what will happen? This particular electron, since now we don't have any vacant p orbital, this electron will jump to 3s and external excitation is not allowed, right? Principal quantum number value should not change. So student, here in case of nitrogen, we won't have excited state. We won't be defining covalency in excited state. So what is the covalency of nitrogen? Covalency of nitrogen is always 3. It can form 3 covalent bonds always. Am I clear? Let's talk about oxygen. How many unpaired electrons? 2 unpaired electrons. So covalency is 2. Since second energy cell don't have a vacant d orbital, this excitation is not allowed. Here also we cannot do this unpairing, right? As soon as if I try to do unpairing, it will jump to 3s and 3p, which is not permitted. So student, for oxygen also, we define covalency only in the ground state, not in excited state. Am I clear, students? Let's move ahead. So for second period elements, if I talk about carbon, the permissible covalency 2, 4. If I talk about nitrogen, the covalency is 3. If I talk about oxygen, the covalency is 2. Covalency is 2 means it can form only 2 sigma or 2 covalent bonds. Am I clear? Okay. For nitrogen, excited state is not possible due to absence of vacant orbital. That's why NCl5 does not exist, because nitrogen cannot form 5 covalent bonds. Same is the story with oxygen also. OF4, OF6 does not exist. The reason is second energy cell don't contain d orbital. Am I clear? Maximum covalency for second period element is 4, and that is for carbon. Already I have discussed these things. Now let's talk about third period elements. Student, from third period onwards, we will have vacant 3D also, right? So here we can do more internal excitation. Let's try to understand. If I talk about phosphorus, the configuration is 1s2, 2s2, 2p6, 3s2, 3p3, right? So in the ground state, how many unpaired electrons are there? The number of unpaired electron is 3. So in the ground state, the covalency of phosphorus is 3. It can form 3 sigma covalent bonds. Now, student, if I talk about the first excited state, can I do the unpairing of this particular paired electrons? So if I do unpairing, it will jump here. One of the electron will jump here. Now how many unpaired electrons I will have? 1, 2, 3, 4, 5. So the covalency of phosphorus in the first excited state is 5. So what is the permissible covalency of phosphorus? 3 and 5. Either phosphorus can form 3 bonds or it can form 5 bonds. Am I clear? Let's move ahead. 3 and 5, it is having a variable covalency. Sulfur, atomic number 16, 3s2, 3p4, right? 3p4. Now, in the ground state, how many unpaired electrons? 2. So in the ground state, covalency is 2. In case of H2S, it has formed 2 covalent bonds, right? Now, covalency is 4 in the first excited state. How? Because I have do the unpairing of this 3p electron. As soon as this 3p paired electron is unpaired, now I will have 4 unpaired electrons. 4 unpaired electrons. So what will be the covalency? Covalency is going to be 4. Am I clear, students? Next one. Still I have one paired system. Can I do the unpairing of this one also? So now this paired electron will also jump. One of the electron will jump to the 3D. Now the total number of unpaired electron is 1, 2, 3, 4, 5, 6. So the covalency is 6. If I talk about sulfur, the permissible covalency is 2, 4, 6. Means it can form either 2 bond, it can form either 4 bond or 6 bond. Am I clear? Shall we move ahead? Let us move ahead. For halogen, let's talk for this chlorine. If I talk about chlorine, how many unpaired electrons do we have in the ground state? 1. Covalency is 1. If I do the first excitation, this paired electron is getting unpaired. So now I will have 3 unpaired electrons. In the first excited state, the covalency is 3. Means all the halogens can form either 1 covalent bond or 3 covalent bond in the first excited state. Still we have unpaired electron. We can do the unpairing of this electron also, right? This one. Now if I do the unpairing of this electron, 3 in NP and 2 in ND. So the total number of unpaired electron will be 5. Covalency will be 5. Means halogen can form either 1 covalent bond, 3 covalent bond or 5 covalent bond. Still we have this ns electron paired, and I can do the unpairing of this ns electron also. As soon as this ns electron is unpaired, the total number of unpaired electron is 7 now. So the covalency will be 7. Means halogen can form either 1, 3, 5 or 7 covalent bonds. Am I clear, students? Let's move ahead. Students, now since we have seen while defining covalency, we always check the number of unpaired electrons. And when these unpaired electrons get paired up, a bond is formed, right? So basically when the two atoms overlaps with each other, when they interact with each other, a bond is formed, and during the bond formation, the unpaired electron gets paired up. Student, we have different theory proposed for this overlapping. The first one that we are going to discuss is valence bond theory. Let's see what does this say. Students, when the two atoms are bonded through a covalent bond, then their half-filled atomic orbital gets combined. Basically, their atomic orbital containing unpaired electrons gets combined and they get paired up, right? Half-filled orbital must have electrons of opposite spin. We have studied this Pauli's exclusion principle, right? Okay. Overlapping of atomic orbitals will always occur along internuclear axis of bonded atoms. This point is also really important. We'll talk about this. Overlapping of orbital will always occur along the internuclear axis of bonded atom. We'll try to understand it. Don't worry. Now student, first of all, let's focus on how does this overlapping occur. This overlapping occurs in two ways. Either head-on overlapping along the internuclear axis or lateral overlapping along internuclear axis. Let's discuss one by one. Head-on overlapping along the internuclear axis or lateral overlapping along internuclear axis. Parallel overlapping, we say it as sidewise overlapping. Am I clear? Let's talk about it. Students, now let's focus on head-on overlap. Students, in head-on overlap, the two atomic orbitals overlap head-to-head along the internuclear axis, and during this head-on overlap, the bond formed is referred as sigma covalent bond. Whenever the two atomic orbitals undergo head-on overlap along the internuclear axis, the bond formed is always a sigma covalent bond. Let's try to understand it in a much more better way. I'm having s orbital. Now these two s orbital is undergoing head-on overlap. As soon as they undergo head-on overlap along the internuclear axis, the bond formed is sigma covalent bond. Am I clear? Okay. Next one, sp overlap. We can see I'm having one of the atomic orbital as s orbital, other one is p orbital. Let's suppose z axis is the internuclear axis and this is z axis. Now along z axis they are approaching. They have undergone head-on overlap, and during this head-on overlap they have formed a sigma covalent bond. A sigma covalent bond is formed between s and pz orbital, right? S orbital and pz orbital, pz, and they have undergone head-on overlap along z axis. Am I clear? Next one, p and p overlap. pz, they are approaching along z axis. As soon as they approach along z axis, they undergo head-on overlap, and whenever we will have head-on overlap, a sigma covalent bond is formed. So student, a sigma covalent bond is formed when s and s orbital undergo head-on overlap, when s and pz orbital undergo overlap along z axis, when pz and pz orbital undergo overlap. In all such case, we'll have the formation of sigma covalent bond. Am I clear? Let's move ahead. Now, sidewise overlap. Atomic orbitals also undergo sidewise overlap, or I say parallel overlap or lateral overlap along internuclear axis. I'm having one py orbital, py, and this particular axis is z axis. Now when they approach towards each other along z axis, what will happen? These two orbitals will undergo parallel overlap, parallel, py. Similarly, px will undergo parallel overlap, and this parallel overlap results in the formation of pi bond. Whenever we will have lateral overlap, this px and this px will undergo parallel overlap. This py and py will undergo parallel overlap when they are approaching towards each other along z axis. So students, this py and py will result in the formation of pi bond. Px and px moving along z axis will result in the formation of pi bond, whereas pz and pz will result in the formation of sigma covalent bond. So student, if we have head-on overlap, we'll have sigma bond. If we have lateral overlap, in that case, we'll have pi bond formation, right? Let's move ahead. Now let's focus on pd overlap. Student, we have studied different types of d orbital, that is dxy, dyz, dxz, dx square minus y square and dz square. Let's focus on dxy. What happens when dxy orbital undergo lateral overlap with py and px? Student, this is the orbital diagram of dxy and this one is py, and they are approaching towards each other along z-axis. Z-axis is the internuclear axis. As they approach towards each other along z-axis, they will undergo parallel overlap. They will undergo lateral overlap. Am I clear? And this lateral overlap will result in the formation of pi bond. Same is the story when dxy undergo lateral overlap with px. Am I clear, students? Let's move ahead. Okay, so whenever this dxy undergo lateral overlap with py, will have the formation of pi bond. When dxy undergo lateral overlap with px, will have the formation of pi bond. dxz with px, pi bond. dxz with pz, pi bond. dyz with py, pi bond. dyz with pz, pi bond. In all such cases, if the internuclear axis, if these axes are the internuclear axis, and whenever we'll have such overlap, we'll have the formation of pi bond. Am I clear? Let's move ahead. dd overlap. I'm having dxy and dxy, right, student? And now let's suppose they are approaching towards each other along x-axis itself. Can I say they will undergo parallel overlap, and this parallel overlap will result in the formation of pi bond itself. dyz, it will also result in the formation of pi bond, and dxz and dxz, they will also undergo lateral overlap only, right? Let's suppose this one is x-axis and this one is z-axis, then it's a dxz and dxz, and these two dxz orbitals are also undergoing lateral overlap, and lateral overlap always results in the formation of pi bond. Am I clear? Let's move ahead. Students, now this one is pi bond. How a sigma bond is formed? Sigma bond is formed by axial overlapping. It is formed by head-on overlapping. Whereas if I talk about a pi bond, it is formed by side-by-side overlapping, lateral overlapping, parallel overlapping. Am I clear? Sigma bond is formed between when the two ss orbital overlaps, when one s, one p orbital overlaps, and one pz and one pz orbital overlaps. In those cases, we will have the formation of sigma bonds. Whereas a pi bond is formed when two p orbital overlaps, when one p and one d orbital overlaps, and when two d orbital overlaps. Am I clear? I hope these things are also clear. Student, in case of head-on overlapping, the extent of overlap is much more higher, and if extent of overlapping is higher, obviously the bond strength will be more, right? Extent of overlapping is less, so relatively pi bond is a weaker bond as compared to sigma bond. Student, if I talk about sigma bond, along the sigma bond, there is always a free rotation. The rotation is not hindered, it's not restricted. We have free rotation. I'm having my atom A, atom B, these two are bonded. I'm having a free rotation. Whereas along pi bond, the rotation is always restricted. Am I clear, students? Let's move ahead. The strength of covalent bond is always directly proportional to the extent of overlapping. More is the extent of overlapping, higher will be the bond strength. Now let's discuss 1-2 questions related to this sigma and pi bond calculation. The total number of sigma and pi bond present in CH3CH, double bonded CH, single bond C, triple bond CH. Okay. CH, double bond CH, single bond C, triple bond CH. Student, if I look at this particular atom, it is bonded to how many atoms? 4 atoms. How many sigma bonds? 4 sigma bonds here, right? 1, 2, 3, 4, 5. If I'm having double bond, the first bond is always a sigma bond, remaining all other bonds are pi bond. So this one is the 5th sigma bond, 6th sigma bond, 7th sigma bond, 8th sigma bond, 9th sigma bond, and 10th sigma bond. So the number of sigma bond is 10. Now 2 pi bonds here, 1 pi bond here. So total number of pi bond is 3. 10 sigma 3 pi. Am I clear, student? Shall I move ahead? Let's move ahead. PP overlapping will be observed in the molecule of. Student, if I talk about hydrogen, it's having 1s configuration. So in case of hydrogen molecule, only 1s atomic orbital will overlap. So whenever you see hydrogen, obviously it is having 1s only. So here I will have 1s p orbital. In case of hydrogen chloride, we have 1s 3p orbital overlapping. In case of chlorine, we have unpaired electron in 2p5. In the ground state covalency, right? We have 2p5 configuration. In one of the p orbital, there was one unpaired electron. So this pp overlapping will be observed in the molecule of chlorine. In chlorine, we'll have pz overlapping, resulting in the formation of Cl2 molecule, ClCl. 1 sigma bond. Am I clear? Whenever this pz and pz will overlap along z axis, we'll have the formation of sigma bond. I hope these things are clear. Let's move ahead. Now this factor is really important. Factors affecting overlapping and bond strength. Student, first, smaller the size of orbital, more is the extent of overlap. This is really important, and more is the extent of overlap, better is the bond strength. So if I talk about this one, 2p 2p, 3p 3p, 4p 4p, and 5p 5p, which overlap will be much better? 2p 2p overlap is more effective as compared to 3p 3p. This 3p 3p is more effective as compared to 4p 4p, and this 4p 4p is more effective as compared to 5p 5p. Smaller the size of orbital, better is the extent of overlapping. Clearly, student, 1s2p here is much more, 1s2p overlap is much more effective as compared to 1s3p. This 1s3p overlap is more effective as compared to 1s4p. Smaller the size of orbital, better is the extent of overlap, higher will be the bond strength. Am I clear? So bond strength depends on size, it's inversely proportional to size of overlapping orbital, because bond strength is directly proportional to extent of overlapping, and extent of overlapping is inversely proportional to size of atomic orbital. Next, factors affecting the bond strength. Bond strength inversely proportional to lone pair repulsion. More is the number of unshared pair of electrons, more will be the interelectronic repulsion, lesser will be the bond strength. Am I clear, students? So you can see here, in case of carbon, the covalency was 4, it's having all 4 sigma covalent bonds, no unpaired electrons, so bond strength is more. In case of nitrogen, we have one unshared pair of electron, so we have certain repulsion, bond strength is relatively less. Whereas in case of OO, I'm having 2 unpaired electrons, 2 pair of unpaired electrons, right? So students, obviously here I will have maximum repulsion, so the bond strength will be relatively less, right? Now this extent of overlapping also depends on the directional nature of orbitals. Let's suppose the principal quantum number is same. The value of n is fixed. Now I am changing the value of L. I am changing azimuthal quantum number value. In that case, student, the extent of overlapping, the bond strength will be directly proportional to directional nature of orbital. More is the directional nature of orbital, higher will be the bond strength. Let us try to understand. If I talk about 2s overlap and 2s2p overlap and 2p2p overlap, this 2p2p overlap is much more effective because p orbital is more directional, right? Whereas s orbital is non-directional. So extent of overlap is much better if the orbital is having a directional behavior. Am I clear? So if the value of n is fixed, higher the value of L, more is the extent of overlap. We can say, or in a better way, always say more is the directional behavior, better is the extent of overlap. So 2p overlap is more effective as compared to 2s overlap, and this 2s overlap is more effective as compared to 2s overlap. Right, student? Similarly here also, this one 2p3d overlap is more effective as compared to 2p3p overlap. This is pi overlap. This pi overlap 2p and 3p. And here I'm having 2p and 3d. d pi, right? Here this d orbital is having a more directional character. So the extent of overlapping, the extent of lateral overlapping in 2p and 3d will be more as compared to the extent of overlapping in 2p and 3p. So the pi bond formed between 2p and 3d will be more stronger as compared to the pi bond formed between 2p and 3p. Am I clear, student? Let's move ahead. Students, now it's time to introduce the concept of hybridization. But before that, let us try to understand the formation of CH4 molecule, which all bonds, which all orbitals are involved, and why there was a need of hybridization. We'll try to understand with this particular example. CH4, the atoms are carbon and 4 hydrogen. One carbon is bonded to 4 hydrogen. Student, if I talk about the covalency, in the excited state, carbon is having a covalency of 4. One electron is present in 2s and remaining all the 3 unpaired electrons are present in 2p. Whereas if I talk about hydrogen, it's having 1s1 configuration, right? So one electron is present in the s orbital. Now, student, if the first, let's talk about the first CH sigma bond formation. 1s1 and carbon, the first electron is unpaired electron is present in 2s. So the first CH sigma bond is formed by the overlap of 1s and 2s, right? 1s and 2s overlap. The next one, second sigma bond, CH second sigma covalent bond, hydrogen 1s, whereas now the next unpaired electron of carbon is present in 2p. So it is formed by the overlap of 1s 2p. The third one, again 1s 2p. Fourth one, 1s 2p. So student, in methane molecule, one sigma bond is formed by the overlap of 1s and 2s atomic orbital, whereas the remaining 3 CH bonds are formed by the overlap of 1s and 2p orbital. Now, the energy or the extent of overlapping of 1s 2s is not equals to the extent of overlapping in 1s and 2p. So can I say the bond length, the bond strength will be differing, right? The 3 CH sigma bonds will have the same bond length, same bond energy, and one of the CH sigma bond will have different bond length and different bond energy. But in practical or in real world, it's not the case. All the CH sigma bonds are having the same bond length, they are having the same bond energy. Now student, in order to explain this phenomenon, the concept of hybridization is introduced. And now let's try to understand the concept of hybridization. Okay, what do you mean by the term hybridization? What is hybrid orbitals? Basically, hybrid orbitals are formed by the intermixing of pure orbitals having almost comparable energy. That whenever these atomic orbitals undergo intermixing, the redistribution of energy occurs to form a new orbital, and the newly formed orbital is almost having a similar shape and same energy. Such a orbital is referred as hybrid orbital, right? Mixing of atomic orbitals having different shape and approximate comparable energy, redistribution of energy to form a new orbitals of same shape and same energy. The newly formed orbital is referred as hybrid orbital, and the phenomenon is called hybridization. Am I clear, students? Hybridization is the mixing of orbital and not the mixing of electrons. This point is really important. Therefore, in hybridization, full filled, half filled, and empty orbitals may also participate. Hybridization is the intermixing of pure orbital. It's not the mixing of electrons. Student, the number of hybrid orbital formed is always equals to the number of atomic orbitals overlapping, undergoing intermixing. If two atomic orbitals will intermix, will have the formation of two hybrid orbitals. Suppose one pure s orbital and one pure p orbital is intermixing. I will have the formation of two pure hybrid orbital or two hybrid orbital, that is two sp hybrid orbital. Am I clear? Suppose one s and two p orbitals are mixing. So how many atomic orbitals are mixing? 3 atomic orbitals. So how many hybrid orbital will get formed? I will have the formation of 3 hybrid orbital, and those 3 hybrid orbitals will be referred as sp2 hybrid orbital. We'll talk about it. After hybridization, the hybrid orbital arrange themselves, and the arrangement of hybrid orbitals is known as electronic geometry of the molecule. So through hybridization only we can predict a geometry of the molecule. Am I clear, student? Let's move ahead. So student, if I talk about this CH4 now, I'm having 2s and 2p. So I'm having 4 unpaired electrons, right? And it's mixing with 4 hydrogen atom having 1s orbital. So basically, student, what's happening? I'm having, how many orbitals are involved here? 1 2s and 3 2p orbitals. So how many orbitals will undergo mixing? 1 2s orbital and 3 2p orbital, s and 3p orbital, right? So the total number of hybrid orbitals formed will be 4, because 4 atomic orbitals are intermixing. 1 2s and 3 2p. Number of hybrid orbital formed will be 4, and I will have the formation of 4 sp3 hybrid orbital. The hybrid orbital formed will be referred as sp3 hybrid orbital, and it's having a shape like this. This is how a hybrid orbital is formed. 1 s orbital and 3 p orbital is overlapping and is forming 4 sp3 hybrid orbital, right? Let's move ahead. And this is the geometry, electronic geometry of a tetrahedral molecule CH4. What's the hybridization? sp3. Why? Because 1 2s and 3 2p orbitals were intermixing to produce 4 sp3 hybrid orbital having similar shape and almost similar energy. Almost, no, completely similar energy. Am I clear? So student, if one s orbital and one p orbital overlaps, intermix, then we'll have the formation of sp hybrid orbital. The geometry is linear. If one s orbital and 2 pure p orbital intermix, that is 1s and px and py, in that case the hybrid orbital formed is sp2. The geometry is trigonal planar, bond angle 120 degree. If one s orbital and 3 p orbital, that is px, py and pz intermixes, will have the formation of 4 hybrid orbital, and the hybrid orbital formed is sp3 hybrid orbital. Hybridization is sp3. Similarly, if one s, 3p and 1d, then the hybridization is sp3d, and in that case geometry is trigonal bipyramidal, like this. This one is a trigonal bipyramidal geometry. We'll talk about this particular geometry in much more detailed way while discussing Bend's rule. Don't worry. Next one. If 1s, 3p and 2d orbital, p orbital involved is px, py, pz, d orbital involved is dz square and dx square minus y square. If these 6 orbitals are combining, 6 hybrid orbital will be formed, and the hybridization of these hybrid orbital will be sp3d2. Geometry will be octahedral. Am I clear, students? Now 1s, 3p and 3d orbitals overlapping, s, px, py, pz, and d orbital involved is dz square, dx square minus y square and dxy. The electronic geometry is pentagonal bipyramidal. Am I clear, student? Let's move ahead. The number of hybrid orbital equals to number of sigma bonds plus number of lone pair on the central atom. This is how we calculate steric number, and through steric number we predict hybridization. Steric number, if it's 2, hybridization is sp. If steric number is 3, hybridization is sp2. Steric number 4, hybridization sp3. Steric number 5, hybridization sp3d. Steric number 6, hybridization sp3d2. Steric number 7, hybridization is sp3d3. Am I clear? Let's move ahead. XeF4. Let's calculate the hybridization and electronic geometry of this molecule. Central atom, xenon. The number of valence electron, 8, right? Okay. How many used in bonding? 4 used in bonding, right? XeF4, 4 used in bonding, right? And total number of electrons, valence electron was 8. So how many unpaired electrons? 4 used in bonding. So 4 unpaired electrons. So can I say we'll have 2 pair of unpaired electrons? So how many lone pair? 2. How many bond pair? 4. Number of bond pair 4, number of lone pair 2, steric number 6, hybridization will be sp3d2. X, E, F, 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 F. This is the electronic geometry of XeF4. 4 bond pair, 2 lone pair. Next one, ClF3. Valence electron 7. How many electrons used in bonding? 3 electrons used in bonding. So bond pair Bp equals to 3. How many unshared electrons? 4. So number of lone pair 2. Steric number, bond pair plus lone pair, steric number 5. If steric number is 5, hybridization sp3d. Geometry trigonal bipyramidal. Am I clear, students? Next one, XeF6. XeF6, it's very important, this particular molecule. How many bond pair? Number of bond pair equals to 6. Number of lone pair 1. So what is the hybridization? sp3d3. Now if the hybridization is sp3d3, you may say, sir, geometry will be pentagonal bipyramidal. But student, this particular molecule is having certain exception. Here the geometry is basically distorted octahedral. XeFF, F and F, and this lone pair remains in the equatorial plane itself. Am I clear? We'll talk about this equatorial plane, axial plane, all these things, don't worry. Next one, XeO3. How many bond pair? Number of sigma bonds equals to 3, right? XeOOO, right? The other bonds are pi bonds. So number of bond pair, actually number of electrons used in bonding is 6. Total number of electron was 8. So number of unshared pair electrons, unshared pair is 1. Now student, in hybridization, we don't consider pi bond. In hybridization, we won't consider pi bond, we'll only count sigma bond. Steric number is always equals to number of sigma bond plus number of lone pair. Lone pair, number of sigma bond is 3 here, lone pair is 1, steric number 4. If steric number is 4, hybridization is sp3. Am I clear? Let's move ahead. Students, now let's talk about the hybridization of molecules containing ions, right? Or let's talk about the hybridization of ionic molecules like NH4 plus CO3 2 minus SO4 2 minus. How do we calculate the hybridization of such molecule? Student, we have a standard formula. First we calculate steric number, and this steric number equals to M plus V minus C plus A divided by 2. What is M? Number of monovalent atom. Monovalent atom. What is V? Valence cell electrons of the central atom. Cell electron of central atom. C. Charge on cation of cation. A. Charge of anion. Anion. Am I clear, students? So steric number is always equals to M plus V minus C plus A divided by 2. If steric number is 2, hybridization sp, 3 sp2, 4 sp3, 5 sp3d. And like that, we calculate a steric number, and through a steric number, we predict hybridization. NH4 plus. Let's try to calculate steric number for this one. M. Number of monovalent atom, 4. V. What is V? Number of valence electrons of the central atom, 5. What's the charge on cation? C, minus 1. Is there any anionic species? No. So A value is 0 divided by 2. 4 plus 5, 9, minus 1, 8 divided by 2, it's 4. Steric number 4, hybridization sp3. So the hybridization of NH4 plus is sp3. Am I clear, student? Let's talk about this I3 minus. Okay. Student, if I talk about this I3 minus, I connected to 2 more I, right? So what's the number of monovalent atom? 2. Right? What is the number of valence electrons on the central atom? 7. Charge of cation, no charge. Charge of anion, 1. Divided by 2. Steric number is 2 plus 7, 9 plus 1, 10 divided by 2, 5. If steric number is 5, hybridization is sp3d. Next one, PO4 3 minus. Number of monovalent atom, 0. Central atom, phosphorus, valence electrons, 5. Charge on anion, 3. 5 plus 3 divided by 2. Steric number 4, hybridization sp3. Am I clear, student? Let's move ahead. So we can calculate the hybridization of each of these molecules, like, right? CO3 2 minus, it's 4 plus 2 divided by 2. Steric number is 3. Hybridization sp2. Let me do for this one also. Valence electrons. The value of V is 5. Monovalent atom, no monovalent atom. Charge on cation, 1. 5 minus 1 divided by 2, 4 by 2, it's 2. Hybridization is sp. In the same way, you can calculate for all these species. Am I clear, student? Let's move ahead. Student, now let's discuss about one more important theory through which we can talk about the shape of a molecule. Through hybridization, we discuss the electronic geometry. Now, since we have studied while studying hybridization that through hybridization we can predict the electronic geometry of the molecule. But what if the molecule is containing lone pair? Lone pair repulsion is much more as compared to bond pair repulsion, right? Students, so if lone pair is present, obviously what will happen? The distortion in electronic geometry of the molecule will occur, and because of that the shape of the molecule will change, right? So for that we have valence shell electron pair repulsion theory. What does this say? Different electron pair present in the valence shell of central atom have a tendency to repel each other. Lone pair repulsion is much more as compared to lone pair, and bond pair repulsion is relatively less. So whenever if only bond pair is present, in that case the hybridization tells us the correct electronic geometry, and electronic geometry and the shape of the molecule is same if no lone pair is present. But if lone pair is present, then distortion will occur. These electron pair arrange themselves to minimize repulsion and maximize distance, right? The next postulate, arrangement of these electron pairs in case of minimum repulsion is referred as electronic geometry of the molecule. And we observe minimum repulsion when we have only bond pairs. Next, arrangement of only bond pair of central atom is known as shape, structure or molecular geometry of the molecule. With the addition of lone pair, there is distortion, so the shape of the molecule changes. Now let's discuss one by one. Student, if the number of bond pair is 2 and the number of lone pair is 0, in that case steric number is 2 only. Hybridization is sp, in that case geometry is linear, even the shape of the molecule is linear. The example BeCl2, right? Let's suppose now I am having steric number 3, means the number of hybrid orbital is 3, 2 bond pair, 1 lone pair. What will happen? I will have 2 bond pair here, 1 lone pair. The shape of the geometry of the molecule is trigonal planar only. Still the geometry is trigonal planar, whereas if I talk about the shape is V shape, bent shaped or angular shape. This is what we observe in case of SO2 molecule, right? If only 3 bond pairs is there, we have studied that, right? If 3 bond pair, then the geometry is trigonal planar. No lone pair, 3 bond pair, hybridization sp2, geometry trigonal planar, shape and geometry is same. Steric number 4, only 4 bond pair, no lone pair. Hybridization sp3, geometry tetrahedral, example CH4, SiCl4, like that. Steric number 4, 3 sigma bonds, 1 lone pair. In that case, geometry is what? Still tetrahedral, but the shape becomes pyramidal. That's what we observed in case of ammonia. Trigonal pyramidal, 3 bond pair, 1 lone pair. NH3, NF3, right? Next one. I'm having 2 bond pair, 2 lone pair. Still steric number is 4. Hybridization is sp3. In that case, geometry will be still tetrahedral. Whenever steric number is 4, hybridization is sp3, geometry is tetrahedral. Shape of the molecule will change with the addition of lone pair. If I'm having 2 bond pair and 2 lone pair, in that case, shape of the molecule will be once again V-shaped or bent shaped or angular shaped. And this is what we observed in case of H2O molecule. OH, 2 bond pair, 2 lone pair. Am I clear, students? Let's move ahead. Steric number 5. All the 5 bonds may be sigma bonds, right? No lone pair. In that case, hybridization is sp3d, geometry trigonal bipyramidal, molecular shape trigonal bipyramidal. Example PF5, PCl5. Student, here the 3 bonds are the equatorial bonds and the 2 bonds, these 2 bonds. These 2 bonds are axial bond. Am I clear? These 2 bonds are the axial bond. They lie above and below the plane. Whereas the 3 bonds, these 3 bonds are in the plane. They are the equatorial bonds. Am I clear? Or they are on the plane. Next one. I can have 4 sigma bond and 1 lone pair. Still steric number 5. Hybridization sp3d. Geometry trigonal bipyramidal. But now the shape will be seesaw. Student, in trigonal bipyramidal geometry, the lone pair will always be present on equatorial position. We'll discuss about it while discussing bent stool. Don't worry. The shape is going to be seesaw. The best example is SF4. 4 sigma bonds, 1 lone pair. Next one. Steric number 5. Hybridization. sp3d only. 3 sigma bonds, 2 lone pair. Type AB3. I'm having ClF3. In case of ClF3, I'm having 3 sigma bonds, 2 lone pair. These lone pairs will be present on equatorial bonds. So student, here the molecular shape will be T-shaped. Geometry is still trigonal bipyramidal, but the shape will be T-shaped. You can see here C, Cl, F and F. And these 2 lone pair. Am I clear? Next one. 2 sigma bonds, 3 lone pair. Type AB2, Hybridization sp3d, geometry trigonal bipyramidal. In that case, the shape will be linear because all the three lone pair will be present on equatorial position. So we'll be able to see only these two bond pairs, and the shape is going to be linear. Best example, I3 minus, right? XCF2. In case of I3 minus, in case of XCF2, the molecular shape is linear. Next one, 6 bond pair, 0 lone pair. Geometry, octahedral. Molecular shape, octahedral. Hybridization, sp3d2. Right? Example, SF6. Or we say it as square bipyramidal. Next one, 5 bond pair, 1 lone pair. Type AB5. Geometry, still octahedral. Shape, the shape will be square pyramidal. In octahedral geometry, the lone pair will be present on axial bonds. So the shape will be a square pyramidal. The best example is XCOF4 or even BRF5. Next one, 4 sigma bonds, 2 lone pair. Type ABF4. Example, XCF4. Students, here the molecular shape will be square planar. 4 sigma bonds on the plane, 2 lone pair above and below the plane on the axial bond. Am I clear? Let's move ahead. Steric number 7. All the 7 sigma bonds, 0 lone pair, type AB7. Hybridization sp3d3. Molecular geometry, pentagonal bipyramidal. Molecular shape, pentagonal bipyramidal. Example, IF7. Next, 6 bond pair, 1 lone pair. Hybridization sp3d3. Geometry will be pentagonal bipyramidal, but here student, in case of XCF6, we say even geometry and the molecular shape as distorted octahedral. Here the lone pair will be present on equatorial bond. Am I clear? The next one, 5 sigma bonds, 2 lone pair, type AB5. Example, XCF5 minus. Here students, XCF5 minus, this one is once again really important, the molecular shape and everything. Geometry, pentagonal bipyramidal. Student, and if I look at this particular molecule, in case of pentagonal bipyramidal molecule, in general, the lone pair will be present. Lone pair will be present on axial bond. Axial bond. Am I clear? Let's move ahead. Friends, now let's discuss hybridization in case of odd electron molecule. In case of odd electron molecule like CF3 dot, 7 electronic species, right? Student, here if the electronegativity of surrounding atom is more than the electronegativity of central atom, then the unpaired electron also participate in hybridization, and this unpaired electron is also treated as one pair of electron. So student, if I talk about this CF3 molecule, here the surrounding molecule is more electronegative as compared to the central atom, right? Here, even though I'm having a single electron, but I will treat it as a pair of electrons. And if I want to calculate steric number, here I will write 3 sigma plus 1 LP. So steric number will be 4, and in that case hybridization in case of CF3 radical, this is really important. Lot of time you may commit mistake. The hybridization is sp3, whereas if the surrounding atom is less electronegative, if surrounding atom is less electronegative like CS3 dot, student, now here hydrogen is less electronegative as compared to carbon. So will electron, this unpaired electron will ignore this unpaired electron, and now we will have steric number equals to 3 only, 3 sigma bonds, right? So hybridization will be sp2 here. Am I clear, student? Let's move ahead. Student, now let's discuss hybridization in case of solid state of few molecules. If I talk about PCl5 solid, student, in the solid form basically it splits into PCl4 plus and PCl6 minus. So the hybridization will be sp3 and sp3d2. PBr5 solid, it will split as PBr4 plus and Br minus. PBr4 plus and Br minus. So what will be the hybridization? sp3. IF5 liquid, right? It will split as IF4 plus and IF6 minus. IF4 plus will have a hybridization sp3d and IF6 minus will have a hybridization sp3d3. I hope these things are crystal clear to you all. Friends, the next topic which we are going to discuss is the comparison of bond angle in different molecule, and this particular concept is once again the VVI concept. Very important concept for all your competitive exam, whether it is JEE mains, advanced or NEET. Everywhere questions are asked on this particular concept. Let's try to understand this bond angle parameter. Factors affecting bond angle. The first one, hybridization. We have understood this hybridization concept, right? We know sp hybridization, sp2, sp3, sp3d, sp3d2 and all these things. We also know how to calculate %s character in a given molecule, right? Now student, this bond angle is directly proportional to %s character. Let's try to understand it. I'm going to take few examples. CH4, C2H4 and C2H2. It's alkane, methane, ethene and ethine. What is the hybridization of carbon here? sp3. What's the hybridization of carbon here? sp2. Alkenes are sp2 hybridized, whereas alkynes are sp hybridized. What is the %s character here? 25%. %s character 33.3%. %s character 50%, right? What is the bond angle in case of acetylene? The bond angle is 180 degree, bond angle 120 degree, bond angle 109.5 degree. You can see directly from here, as the %s character is increasing, the bond angle is also increasing. So with increase in the %s character, electronegativity increases. With increase in the electronegativity of the central atom, the bond angle increases. Am I clear? Let's move ahead. BeCl2, BCl3, CCl4. What's the hybridization here? sp3, bond angle 109.28, 109 degree 28 minutes. BCl3, sp2 hybridization, right? 3 sigma bond, sp2, bond angle 120 degree. Molecule geometry, trigonal planar, so the bond angle is 120 degree in case of BCl3, whereas BeCl2, linear molecule, the bond angle is going to be 180 degree. sp hybridization, more %s character, more %s character, more is the bond angle. Okay, NO2 plus and NO3 minus. Let's do it, this one also. If I talk about the hybridization of NO2 plus, the hybridization is sp. Whereas in case of nitrate, NO3 minus, the hybridization is sp2. If the hybridization is sp2, geometry will be planar, bond angle will be 120. Whereas if the hybridization is sp, geometry is going to be linear, bond angle 180. More is the % character in case of NO2 plus. So bond angle of NO2 plus will be more as compared to the bond angle of NO3 minus. Am I clear? Shall I move ahead? Let's move ahead. Now, bond angle also depends on the number of lone pair present on the central atom, right? More is the number of lone pair present, lesser will be the bond angle. If all the other parameters are same, suppose if the hybridization is fixed, with increase in the number of lone pair, in general the bond angle decreases approximately by 2.5 degree. For one lone pair, the bond angle decreases by a factor of 2.5 degree. Let's try to understand. More is the number of lone pair on the central atom, lesser is the bond angle. CH4, no lone pair, bond angle 109 degree 28 minutes, right? NS3, one lone pair, bond angle is 107 degree. So with the addition of one lone pair, the bond angle is decreasing by a factor of 2.5 degree. H2O, one more lone pair is present now, two lone pair, the bond angle will further decrease and now the bond angle is 104.5 degree. Once again, bond angle has decreased by a factor of 2.5 degree. Right, student? So with the addition of lone pair on the central atom, the bond angle decreases. Am I clear? Shall we move ahead? Let's move ahead. Electronegativity of the central atom. Student, if the surrounding atoms are same, with increase in the electronegativity of central atom, the bond angle increases. When in a given molecule, the hybridization is same, the number of lone pairs on the central atom is same, then bond angle is directly proportional to electronegativity of central atom. This point is once again important. H2O, H2S, every parameter is same, hybridization is, everything is same. Oxygen more electronegative. What will be the bond angle? Bond angle of H2O will be more as compared to the bond angle of H2S. Central atom more electronegative, higher bond angle. Am I clear? OCl2, SCl2, SeCl2. Down the group, electronegativity decreases. With decrease in the electronegativity of central atom, the bond angle will decrease. So bond angle will be more in case of OCl2, then in case of SCl2, and then in case of SeCl2. The bond angle, let's suppose it's theta, theta 1, theta 2, theta will be greater as compared to theta 1, more greater as compared to theta 2. Every other parameters are same, surrounding atom is same. With increase in the electronegativity of the central atom, the bond angle increases. Now, size/electronegativity of the surrounding atom, or we say it as terminal atom. Student, when in a given molecule, hybridization of central atom is same, the number of lone pair on the central atoms are same, then with increase in the electronegativity of the surrounding atom, the bond angle decreases. With increase in the electronegativity of surrounding atom, the bond angle decreases. With increase in the size of surrounding atom, the bond angle increases. Am I clear? With increase in the, if other parameters are same, if the surrounding atoms are more electronegative, then the bond angle will be more. Am I clear? Let's try to understand. Bond angle is directly proportional to size of surrounding atom and inversely proportional to electronegativity of surrounding atom. This parameter is once again really important. See, as the size of terminal atom will increase, obviously the steric crowding will increase. So the molecule will expand, bond angle will increase. Now, if the surrounding atoms will be more electronegative, electron density on the central atom will be less. And if electron density will be less, interelectronic repulsion will be less, right? Bond angle will be less. So with increase in the electronegativity of surrounding atom, bond angle decreases. With increase in the electronegativity of central atom, bond angle increases. Now OF2, OCl2, OBr2, OFF, OClCl, OBr, right? Which one is more electronegative? OF2, surrounding atom is fluorine here. Here it's chlorine. Here it's bromine. With increase in the electronegativity of surrounding atom, the bond angle decreases. So in which case you will find more bond angle? In case of OBr2. One more factor. With increase in the size of surrounding atom, the bond angle increases. Bromine, larger in size, bond angle will be more. Am I clear? Student, one very interesting case here. We have to compare the bond angle of BF3, BCl3, BBr3 and BI3. A very special case. Very important. Student, now you will say the central atom is same. Hybridization is also same. Everywhere it's sp2 hybridized only. Now, if central atom is same, with increase in the size of surrounding atom, the bond angle should increase, right? So in case of Bi3, the bond angle should be more. But student, one very important point. If central atom is same, right, and if the molecule is symmetrical, if central atom is same, central atom same, hybridization same, molecule symmetrical or planar, better say planar, because planar molecules are highly symmetrical, right? They do have plane of symmetry. If the molecule is symmetrical, even though if I will increase the size of surrounding atom, the bond angle will not change. So here, in case of BF3, in case of BCl3, BBr3, Bi3, everywhere the bond angle is going to be 120 degree. Irrespective of the electronegativity of surrounding atom, irrespective of size of surrounding atom. Am I clear, students? I hope this particular concept is also clear. Now, when the surrounding atom is, if surrounding atom is fluorine, surrounding atom is fluorine, then consider factor of electronegativity while comparing bond angle. Then don't consider the factor of size. Am I clear? Let's take one example. Suppose I have to compare the bond angle of NH3 and NF3. F. Everywhere. Here also the hybridization is sp3. Right? 3 bond pair, 1 lone pair, 3 bond pair, 1 lone pair. Every parameter is same, central atom is same, number of lone pair is same. Now here the surrounding atom is hydrogen, surrounding atom is fluorine. Fluorine is larger in size as compared to hydrogen, right? So if I consider the size factor, then the bond angle in NF3 should be higher. But student, if fluorine is the surrounding atom, this fluorine is highly electronegative. Here the role of electronegativity will dominate over size factor, and in this case, student, since fluorine is a highly electronegative element, the electron density will be less on the central atom. With decrease in the electron density on the central atom, the bond angle decreases. So bond angle in ammonia will be more as compared to NF3. Am I clear? Same story in case of H2O and OF2. OHH, OFF. Every parameter is same. 2 lone pair, 2 bond pair, 2 lone pair, 2 bond pair. But here hydrogen, here fluorine being more electronegative, electron density on oxygen will be less. So bond angle in H2O will be more as compared to OF2. So these 2 points are really important. If I have to compare the bond angle of NF3, NH3 and NCl3, bond angle will be least in NF3, then NH3 and then NCl3. Between NH3 and NCl3, consider size factor. Between H2O and Cl2O, consider size factor, right? But between these two molecules, consider the factor of electronegativity. Am I clear, student? Shall I move ahead? Let's move ahead. In the hydrides of 15th and 16th group, except NH3 and H2O, the value of bond angle will be approximately equals to 90 degree. Yes, it's basically Drago's rule. Mainly in such cases, in case of PH3, ASH3, SBH3, BIH3, in all such cases, bond angle is close to 90 degree. Drago's rule is applicable. Here, the concept of hybridization fell. All these pH bonds are having 100% p character, and this lone pair is present in purely s orbital. So this lone pair is having 100% s character, whereas this pH bond is having 100% p character. And if it's a pure p character, 3 p orbitals, so all these p orbitals, px, py and pz, they are at 90 degree. That's why the bond angle is close to 90 degree in these cases. Similarly, in case of H2S, H2TE, all these cases bond angle is close to 90 degree. Am I clear, student? Let's move ahead. NH3, the bond angle is 107, whereas in case of PH3, bond angle is 93. In all three cases, you will see bond angle close to 90 degree. All PH bond, all ASH bond are having almost 100% P character. Similarly, H2S, H2SE, H2TE, in all such cases, the bond angle are close to 90 degree, right? The concept of hybridization fails. Here, all the HS bonds are having pure P character, right? Let's move ahead. Student, let's do some questions related to this bond angle concept. This piece is having bond angle of 120 degree. ClF3. What is the hybridization in case of ClF3? Central atom chlorine, number of valence electrons 7, 3 sigma bond, 7 plus 3 10, steric number is 5, hybridization is going to be sp3d, right? Okay. In case of BCl3, number of sigma bonds 3, number of lone pair 0, hybridization sp2. If the hybridization is sp2, geometry is trigonal planar and the bond angle is close to 120 degree. NCl3, 3 sigma bond, 1 lone pair, sp3, bond angle is close to 109.5 degree. Then PH3, here Drago's rule is applicable, bond angle is close to 92 degree. So in which of the following case the bond angle is 120? In case of BCl3. Am I clear, student? Let's move ahead. Comparison of bond length. Now, what is this bond length? It's basically the internuclear distance between the two atoms, two covalently bonded atoms. In a better way, we can define it like this: internuclear distance between two covalently bonded atoms. This particular distance is nothing but bond length. I'm having an atom A, B. This is the nucleus of atom B. This is the nucleus of atom A. They two have overlapped. They have formed a covalent bond. Now, the internuclear distance between these two covalently bonded atoms is bond length. Am I clear? This bond length is inversely proportional to percent S character. More is the percent S character, more is the electronegativity, better will be the overlapping, lesser will be the internuclear distance, lesser will be the bond length. So bond length inversely proportional to percent S character. Student, now related to this bond length parameter, we have one very important rule referred as Bend's rule. Student, if I talk about this sp3d hybridization, how this sp3d is formed? It's formed through by the combination of sp2 plus pd. Now, if I look at the geometry of this sp2 hybridized orbital, it's like this one, trigonal planar. Whereas if I look at this pd overlapping pz and dz square, it will be like this. Am I clear? So this is the geometry of a sp3 hybridized orbital atom, right? sp3d. If I look at this particular geometry, here students, we have three equatorial bonds, M, A, B, B. These Ma bonds are lying in the plane. If any bond is lying in the plane, it is referred as equatorial bond. So all these bonds, these PCl bond, this one and this one, these Ma bonds are lying in the plane. So what's the bond angle here? The bond angle is 120 degree. M, A, right? So bond angle, and these three are the equatorial bond. Whereas if I talk about this MB, this one is referred as axial bond. axial, axial. One of the bond is lying above the board and the other one is into the board. Am I clear? These two bonds are referred as axial bond. One lying above the board, one lying below the board. Now, what's the bond angle between axial, axial? 180. Axial and equatorial. What is the bond angle? Between axial, axial, it's 180. Axial, equatorial. Everything is in the plane and now this one is above the plane. So what's the bond angle? 90 degree. So axial, equatorial, 90 degree. Equatorial, equatorial. How much? 120 degree. So where do you find more spacing? Equatorial, equatorial or axial, equatorial? Equatorial, equatorial. Spacing is more. The bond angle is 120 degree. Whereas the spacing is less on axial equatorial because the bond angle is 90 degree. So can I say, students, the bulkier groups will occupy or will be placed on equatorial position, right? Student, in sp3 hybridized system, equatorial bonds have more percent s character because this s orbital is more bulky as compared to the p, or the axial bonds have more percent p character. Equatorial have more percent s character, axial have more percent p character. So if you have to place a lone pair, this lone pair is a bulky group, where will you place it? On the equatorial bonds in case of sp3 hybridization, right student? Let's see. So percent s character is more on the equatorial bond, and if the percent s character is more, the bond length will be less. So in this trigonal planar geometry, equatorial bond length is smaller as compared to axial bond length because axial bond length is having more percent p character. This p orbital is longer and thinner. That's why axial bond is longer as compared to the equatorial one, right? Species having sp3 hybridization will have two types of bond length, axial and equatorial bond length will be smaller as compared to the axial one. Student, this is also really important. In a particular molecule, suppose if the hybridization is sp3d, right? You are having a trigonal planar geometry. In that case, where will you place the more electronegative element? Student, always remember the more electronegative elements will always be placed on axial bonds because more electronegative elements in general are placed to the orbital containing more percent p character, right? So student, this more electronegative elements will occupy those orbital for bonding having less percent s character or more percent p character. PCl3F2 hybridization sp3d geometry like this, right? So you are having three equatorial, two axial. You will place fluorine on the axial, whereas chlorine atoms on the equatorial. This is having more p character. Am I clear, student? More p character here, more s character. Less electronegative multiple bonds or lone pair will always occupy those orbitals having high percent s character. In general, in a trigonal planar geometry, lone pair is always placed on the equatorial bonds. Am I clear? Lone pair, equatorial. Okay. Friends, moving ahead, the next topic which we are going to discuss is once again one of the most important topic, and it is dipole moment. Once again, a very important topic. VVI. Actually, all the topics in chemical bonding chapter are really important. This chapter, chemical bonding is itself the most important chapter of chemistry. If this particular chapter is crystal clear, entire inorganic as well as organic will be crystal clear to you all. You won't have maximum problem or much problem while doing GOC and all these things. Student, now let's try to understand dipole moment. Student, lot of time we say like dissolves like. Polar molecules are soluble in polar solvent. Non-polar molecules are soluble in non-polar solvent. But how do we say whether a given molecule is polar or non-polar? In order to predict the polarity of molecule, we use the concept of dipole moment. Polarity of a covalent molecule is always measured in terms of dipole moment. Polarity of a covalent compound directly proportional to electronegativity difference between two covalently bonded atoms. Higher is the electronegativity difference between two covalently bonded atoms, higher will be the polarity, and higher is the polarity, higher will be dipole moment. If the electronegativity difference between two covalently bonded atoms is 0, in that case molecule will be non-polar. Am I clear? If delta En equals to 0, molecule is non-polar, mainly homodiatomic species. H2, Cl2, Br2, I2, all these diatomic molecules, the electronegativity difference is 0. So molecule is non-polar. Am I clear? If electronegativity difference is non-zero, molecule will be polar. HF, HCl, HBr. There is certain electronegativity difference between hydrogen and fluorine. So molecule is polar. Now which one is more polar? That we decide on the basis of dipole moment represented by the symbol mu. Okay, let's talk about it. It's directly proportional to dipole moment, right? Now how do we calculate it? Dipole moment of any molecule, it's simply calculated as dipole moment mu is always equals to charge into separation distance between or the bond length of the molecule. Suppose I am having a molecule A and B, and let us assume this B is more electronegative. So I will have delta negative over here and delta positive over here, right? Because the sigma electrons cloud will be pulled by this B. B being more electronegative will try to pull all the sigma electron cloud towards B. And if it is pulling all the sigma electron cloud towards itself, it will be electron rich. So I will have del negative. So now this A will become electron deficient. I will have del positive charge appearing on A. Now we calculate dipole moment of this molecule AB as this charge into the bond length of AB. Am I clear, students? Okay. A, B, del negative, del positive. A dipole is created. Same charge, negative, del negative, same magnitude of charge, del positive. A dipole is created. Now, dipole moment is nothing but charge into distance, Q into D. Basically, it's a vector quantity. Charge induced on a covalently bonded molecule due to electronegativity difference. If there is no electronegativity difference, then there won't be any charge induced. We won't have any partial charge appearing. Q will be 0. Dipole moment will be 0. Am I clear? And D is the internuclear distance. Let's move ahead. Student, this dipole moment is a vector quantity and the direction is always towards more electronegative element. Suppose I am talking about the dipole moment of this HF. This fluorine more electronegative, it will pull all the sigma electron towards itself. I will have del negative, del positive. Now the direction of the dipole moment is always towards more electronegative element. The direction of this vector is always towards more electronegative element or more electronegative atom, from less En to more En atom. Am I clear? Okay. In case of lone pair, the direction of mu is from central atom towards lone pair, like this. Suppose I am having NH, H, H. Now, here in ammonia molecule between hydrogen and nitrogen, nitrogen is more electronegative, and here I am having a lone pair also, right? So a dipole is created between this NH bond. And if I talk about the direction of this dipole, it will be towards more electronegative element, mu1. Same here, it will be towards more electronegative element. Same magnitude of dipole will be there because the atom is same, mu1. Same magnitude of dipole moment will be there because the atom is once again same nitrogen and hydrogen, and the direction will be from hydrogen towards nitrogen, mu1. Now between this nitrogen and lone pair, once again a dipole is created, and now the direction of this dipole is from central atom towards lone pair, mu2. The magnitude will be different because the atoms are different. One is nitrogen and the other species is lone pair. Am I clear, students? If I talk about the unit of dipole moment, the unit is debye, and 1 debye equals to 1 into 10 raised to the power minus 18 electrostatic unit. This one is once again really important. Please even copy this one also. Let's move ahead. Student, we have already discussed for diatomic molecule, this dipole moment is simply dependent on charge. More is the electronegativity difference, more will be the charge induced, higher will be the dipole moment. HF, HCl, HBr, HI, they are diatomic molecule. HF, HCl, HBr, HI. Now you will say, so this dipole moment mu is basically Q into D. As I am moving from HF to HI, bond length is increasing. But student, for diatomic molecule, you need to consider only charge factor. Charge is the more dominating factor. This factor is more dominating. Electronegativity factor, which is causing del positive and del negative. Fluorine, most electronegative, I will have maximum del positive. More is the del positive, higher will be the mu. Am I clear? Let's move ahead. For polyatomic molecule or polyatomic molecule, more than two atoms are involved. In that case, mu net is equals to vector sum of dipole moment present in polyatomic molecule. Right? A, B, C, this molecule is there. Between A and B, the dipole moment is mu1. Between A and C, the dipole moment is mu2. Now here, mu net equals to mu1 square plus mu2 square plus 2 mu1 mu2 cos theta, where theta is the bond angle. We have studied the resultant vector, right? If A vector, B vector, the resultant one is under root A square plus B square plus 2AB cos theta, right? Okay. Student, if mu net, if the net dipole moment of a molecule is 0, the molecule is non-polar. This is really important. Whereas if mu net is non-zero, the molecule is polar. Okay, one more important point. If theta equals to 0, we have studied this mu net equals to under root mu1 square plus mu2 square plus 2 mu1 mu2 cos theta. Right? Okay. And this cos theta, if it's 0 degree, then it's mu1 square plus mu2 square plus 2 mu1 mu2. Right? So basically it's mu1 plus mu2 whole square under root. So it's basically mu1 plus mu2. Am I clear? And in that case, the dipole moment will be maximum. If the two dipole moments are in the same direction, if the bond angle is 0 degree, they will simply get added and the dipole moment will be maximum. Whereas if theta is 180, obviously it will be minimum. They will try to cancel out each other. Like BeCl2. You can see one of the mu1, they are at 180 degree. So mu net 0. Molecule non-polar. We'll talk about it. CO2, just now we have discussed. Mu1, mu2. One in this direction, one this direction. The bond angle 180. These vector will cancel out each other. Atom is same, so the magnitude will be same. Direction opposite. They will simply cancel out each other, and CO2 is a non-polar molecule. Here BF3, although here student, the bond angle is not 180 degree. Here the bond angle is 120 degree, but the molecule is symmetrical. 120, 120, 120. In all the BF bonds, the dipole moment is going to be same. Atom is B and F only. Mu1, mu1, mu1. And these three vectors having the magnitude mu1, mu1, mu1 are at 120 degree. Mu1, 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 120 degree. Can I say the resultant of these two mu1 will be in this direction and will have a magnitude mu1 only because the bond angle is 120. Mu1 square plus mu2 square plus 2 mu1 mu2 cos theta. Am I clear? So the resultant will be mu1 only. Now these two mu1 and mu1, they will cancel it out each other. So here also in case of BF3 also mu net is 0. So if the molecule is symmetrical, molecule is planar, in that case, dipole moment is 0 and the molecule becomes non-polar. Am I clear, student? Let's move ahead. Other example of non-polar molecule CH4. Once again, symmetrical, plane of symmetry is there. PCl5 molecule is symmetrical. 3 like this and these two like this. Axial will cancel out each other. These two equatorial and this equatorial will cancel out each other. So in PCl5, same in SF6, same in IF7. In all such cases, mu net will be 0 and molecule will be non-polar. If in a molecule, if the central atom has lone pair, then it will be polar and mu won't be equals to 0. Yeah, NS3. Right, central atom is having a lone pair, so obviously there will be certain dipole moment observed. This one cannot be 0, even though if they cancel out each other, this one from central atom towards lone pair, this one won't be 0, and we will have certain dipole moment and the molecule will be polar. If dipole moment is 0, molecule non-polar, non-zero, molecule polar. Friends, moving to the next case, and this particular case is if the molecule side atoms are different, then it may be polar or non-polar depending on vector sum. Let's do one example related to this one. PCl3F2. Okay, we have to check the dipole moment of this molecule. PCl3F2, both the fluorine will be placed on the axial bond and chlorine will be placed at equatorial bond, right, student? Now between P and Cl, let's suppose the magnitude of dipole moment is mu2. So mu2, 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 three vectors at a bond angle of 120, each having magnitude mu2, 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 right, student? Now can I say the resultant of these two vectors will be mu2 only, but in this direction, and these two mu2 will cancel out each other. What's the net dipole moment on this equatorial one? 0. Now P and F, it will have a, here also will have one dipole observed, and here the dipole moment is mu1 because the atom is fluorine now. The atom is changed, so charge will be changing, the bond length will change, so the magnitude of dipole moment will be changing, and now here it's mu1. One vector in this direction having magnitude mu1, other vector exactly at 180 degree, once again having magnitude mu1. These two axial will also cancel out each other and mu net will be 0, molecule will be non-polar. Am I clear? Let's move ahead. PCl2F3. Now we have 2 chlorine atom and 3 fluorine atom. 2 of the fluorine atom will be placed on the axial bond, and one of the remaining fluorine atom will be placed at equatorial one. Okay, now I'm having 2 chlorine atom also, and they are placed at equatorial only, right? Now, student, if let's talk about this one, P and Cl, the dipole moment is mu2, magnitude. P and Cl, magnitude wise dipole moment is mu2. So I'm having, and P and F, the magnitude wise dipole moment is mu1. So now my situation is like this, geometry is like this. One of the vector having magnitude mu1 in this direction, other two vectors having magnitude mu1 and mu1 in opposite direction, so they will cancel out each other. Now two vectors having magnitude mu2, PCl, PCl, so their resultant vector will have a magnitude mu2 only in this direction. Now, uh, basically I am having two vector, one having magnitude mu1 and other having magnitude mu2 but in opposite direction at 180 degree. What will be the resultant vector? Mu1 minus mu2. Since the magnitude is not same, they will not cancel out each other. Mu net will never be 0 and the molecule here will be a polar one. So PCl2F3 is polar whereas PCl3F2 is non-polar. Let's move. Students, now certain time we are asked to compare the dipole moment of NH3 and NF3. This particular question is also really important. NH3 and NF3. If we look at the structure of NH3, dipole moment mu1, mu1, mu1 and mu2, and all of them are getting added. They all are pointing in the same direction. Hydrogen to nitrogen in this direction, hydrogen to nitrogen this direction, hydrogen to nitrogen this direction, nitrogen to lone pair this direction. All are pointing in the same direction. So they will get added and mu net will not be equals to 0. So the molecule will be polar only. Even this NF3 will also be polar. But here, let's see the direction of dipole. From nitrogen to lone pair, upward mu2. Nitrogen to fluorine, downward, nitrogen to fluorine, downward. Three vectors pointing in the downward direction, one vector pointing in the upward direction. In which case, mu resultant will be more. In case where it is getting added. So the observed dipole moment of NH3 will be more as compared to NF3. Am I clear, students? Let's move ahead. Similarly, NH3 and NBr3, same story, right? NH3 and PH3. Now this is important. Student, if I talk about this PH3, the electronegativity of P and H is almost same. P and H, electronegativity difference delta En equals to 0. And if there is no electronegativity difference, obviously here we won't have any dipole observed. Mu till in all the pH bonds will be 0. It will be observed only in P2 lone pair, right? So the dipole moment will be mu2 only. If I talk about this NH3, here it's mu1, mu1, mu1 and mu2 and all of them are getting added, right? So here obviously the resultant dipole moment will be more. So the dipole moment of NH3 is more as compared to that of PH3. This one is also important. Next, which of the following compound has maximum dipole moment? SO3. Molecule geometry is like this. Symmetrical molecule, mu1, 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 all at a bond angle of 120. Mu net equals to 0. PCl5, mu net equals to 0, non-polar molecule. CCl4, mu net equals to 0. NF3, in case of NF3, no doubt dipole moment will be less as compared to NH3, but still mu net will not be equals to 0. So dipole moment will be observed, and among these molecules, NF3 will have maximum dipole moment. Am I clear? Let's move ahead. Which of the following sequence of dipole moment is correct? NS3, NF3, BF3. BF3, NF3, NS3. If I talk about BF3, molecule symmetrical, so mu equals to mu net equals to 0. NH3, we have just now studied mu of NH3 is greater than mu of NF3. So can I say the dipole moment will be in the order NH3 max, then NF3, and then least in case of BF3. Am I clear, students? Let's move ahead. Some important order of dipole moment, and this is really important. VVI once again. Student, if I have to compare the dipole moment of CH3Cl, CH3F, till yet I was talking that charge is a dominating factor, but in CCl bond, charge into distance will overall dominate between chlorine and fluorine. Otherwise, in other cases, once again charge will be dominating factor. But between CF and Cl, Q into D of this CCl will dominate over Q into D of CF. So dipole moment of CH3F is smaller as compared to the dipole moment of CH3Cl, because there is no much electronegativity difference between fluorine and chlorine. Electronegativity difference is comparable and size is more in case of chlorine. So Q into D of CCl bond will dominate over Q into D of CF, and dipole moment of CH3Cl will be greater as compared to CH3F. Now once again, charge is a dominating factor. So dipole moment of CH3Br will be less as compared to CH3F, and dipole moment of CH3I will be less as compared to CH3Br. Am I clear, students? Next one. And one more important example is there, and that CCl4, CHCl3, CH2Cl2 and CH3Cl, right? Okay. Student, if I have to compare the dipole moment is 0 in case of CCl4. Whereas in all other cases like CHCl3, then CH2Cl2, CH3Cl, in all such case the dipole moment is non-zero, and the order of dipole moment is it's maximum in case of CH3Cl, then CH2Cl2, and relatively lesser in case of CHCl3, and 0 in case of CCl4. This order is also really important. Lot of time this particular question is asked. Let's move ahead. Now, application of dipole moment. If dipole moment mu net equals to 0, molecule is polar, molecule is symmetrical. Symmetrical molecules are non-polar. If mu net equals to 0, molecule is non-polar and it's symmetrical. If mu net not equals to 0, molecule is unsymmetrical. Right? Okay. Student, if I have to compare in geometrical form, we have two different forms, cis form and trans form. In general, the dipole moment of cis form is more as compared to the dipole moment of trans, because in trans configuration, the two similar groups, they are at anti-position with respect to each other. So the vectors cancels out each other, whereas in case of cis, these two vectors will get added. Am I clear? Let's move ahead. So dipole moment of cis is greater in general as compared to the dipole moment of trans. This form is more polar as compared to the trans form. Here, student, I am having CH3Cl and CH3Cl. Now, this is the exceptional case. See, this one is also cis trans only, but here, if we look at the dipole moment, that's why I always say, whenever you have to compare the dipole moment, always write the geometry and then only compare. Because if you remember, in general, I have told you the dipole moment of cis is greater than that of trans. But if you look here, the vector is going from C to C, right? And here also the vector is going from C to Cl. So I'm having two vector, mu1 going in this direction and mu2 in this particular direction, right, student? Whereas if I look at this transform, mu1 going in this direction and mu2 also going in the same direction, so the bond angle is 0, so these two vectors will get added, and here the dipole moment of trans will be more as compared to that of cis. Let's move ahead. Student, similarly in case of substituted benzene, the dipole moment of ortho is more as compared to the meta one, and the dipole moment of meta is more as compared to para, because in case of para, the two vectors may cancel out each other and mu net may approach to 0 and the molecule may become non-polar. Am I clear, students? You can see here, Ortho dichlorobenzene, it's having more dipole moment as compared to meta dichlorobenzene, and meta dichlorobenzene is having more dipole moment as compared to the para. With increase in theta, as theta increases, cos theta value will decrease, dipole moment will decrease. Am I clear? Let's move ahead. Student, now if I talk about the application of this dipole moment, through this dipole moment, we can calculate the percent ionic character of any covalent compound. We can calculate percent ionic character of a covalently bonded molecule. And this percent ionic character is calculated by the formula. Percent ionic character equals to experimental value of mu, that is mu observed upon mu calculated, Q into D into 100. Mu observed or mu experimental upon mu calculated into 100. This is how we calculate the percent ionic character of any covalently bonded molecule. Okay. Calculate the percent ionic character or charge fraction in a molecule in which the bond length is 1 angstrom and charge equals to 4.8 into 10 raised to the power minus 10 ESU. Given the experimental value of dipole moment is 1.2 D. So student, mu observed is how much? 1.2 dBi. Okay. What mu theoretical? Mu theoretical is always equals to Q into D. Charge into distance. Right? What is the charge? Charge is equals to 4.8 into 10 raised to the power minus 10. Student, 1 dBi is basically, it's represented in terms of ESU centimeter. And here the distance is given in terms of angstrom. 1 angstrom equals to 1 into 10 raised to the power minus 8 centimeter. So Q is 4.8 into 10 to the power minus 10 ESU into 1 into 10 raised to the power minus 8 centimeter. Now this one is 10 raised to the power minus 18 ESU centimeter. 1 into 10 raised to the power minus 18 ESU cm is equals to 1 dBi. So it's how much? 4.8 dBi. So mu theoretical is equals to 4.8 dBi. Mu observed is 1.2. Percent ionic character 1.2 divided by 4.8 into 100. So it's 25%. Am I clear? Shall we move ahead? Let's move ahead. Before moving to this molecular orbital theory, let's first of all talk about the failure or the drawbacks of valence bond theory. Why there was a need of molecular orbital theory? What are the things which valence bond theory could not explain? Student, if I talk about the drawbacks of valence bond theory, the first one, it could not explain the magnetic behavior of certain diatomic species. It could not explain why oxygen is having a paramagnetic behavior, right? It could not explain the fractional bond order in certain diatomic species. Why the bond order is 1.5, why the bond order is 2.5. It could not explain the fractional bond order. At the same time, it could also not explain existence and non-existence of certain diatomic species. Why He2 does not exist? Why Be2 does not exist? It could not explain the existence of these diatomic or non-existence of these diatomic species. Students, for these things we needed one more theory, and now we are going to discuss that one, and that is molecular orbital theory. So let's discuss the postulates of molecular orbital theory. Okay, let's first of all read one by one. Student, as the electrons of an atom are present in its atomic orbital, similarly electrons of a molecule will be present in the molecular orbital. Electrons are nothing but standing wave and they are present in atomic orbital. And now when these two atomic orbitals combine, they give or they lead to the formation of molecular orbital. So similarly, as the electrons is present in atomic orbitals of an atom, in a molecule the electron will be present in the molecular orbital. Okay, When two atoms combine through a covalent bond, then their atomic orbital of almost same energy and same symmetry gets combined, and they results in the formation of molecular orbital. Basically, two atomic orbitals of comparable energy and similar symmetry results overlaps, and they combines, and their combination results in the formation of molecular orbital. The number of molecular orbital formed is always equals to the number of combining atomic orbitals. If two atomic orbital will combine, I will have the formation of two molecular orbital. 2AO combination will give us two molecular orbital. The number of molecular orbitals combining or number of molecular orbitals formed is always equals to the number of atomic orbitals combining. Am I clear? Let's move ahead. Students, now this electron is nothing but a standing wave, and these electrons are there in atomic orbital. So we are going to consider these atomic orbital also as also having a wave nature itself. Now, when these two waves, these two atomic orbital will overlap, they may overlap in phase, positive, right? They may overlap out of phase, one positive and the other negative, right? And when these two waves overlaps, basically we have two types of molecular orbital formed. If similar phase orbitals are, atomic orbitals are overlapping, we'll have the formation of bonding molecular orbital. Plus, minus, similar type, right? Same phase atomic orbital overlap results in the formation of BMO, whereas out of phase atomic orbital overlap results in the formation of ABMO. These atomic orbitals are nothing but a pure wave. Now, if these two waves will overlap, they may undergo constructive interference. Similar, same phase overlap, that is constructive. Out of phase overlap, that is destructive. Plus, constructive, plus, minus, destructive. Am I clear? If these two overlap will occur, I will have destructive interference. It will lead to the formation of ABMO. Whereas plus, minus, same phase overlap, it's a constructive interference, will have the formation of BMO, bonding molecular orbital, anti-bonding molecular orbital. Am I clear? Student, now let's first of all talk about this bonding molecular orbital and anti-bonding molecular orbital. Bonding molecular orbital is the result of combination of atomic orbitals when their wave functions are in same phase, plus overlap, right? If plus overlap is there, obviously the amplitude will increase, the electron density will increase. Am I clear? If one of the atomic orbital is having a wave function psi A, another psi B, since it's a constructive interference, same phase overlap, the resultant will have a wave function psi A plus psi B. That's why the amplitude has increased. It's a constructive interference. Bonding molecular orbital is simply formed through constructive interference. When two out of phase atomic orbital overlaps, it results in the formation of destructive interference. Such a interference, such a superposition is DI, and through DI we will get anti-bonding molecular orbital. Anti-bonding molecular orbital is the result of combination of atomic orbital when their wave functions are in opposite phase, plus minus, overlaps results in DI, and this DI gives us ABMO. Am I clear? Electron density increases in between the two nucleus. Obviously, in case of constructive interference, what will happen? The electron density in between the nucleus will increase, and because of that, the attractive force will increase. And whenever attractive force increases, the potential energy decreases, stability of the molecule increases. So BMO will have less energy, more stability. Whereas in case of ABMO, electron density decreases between two nucleus. If the electron density between the nucleus is less, repulsive force between the two nucleus will be more. And because of that, potential energy will be more, stability will be less. So in case of ABMO, PE is more, stability of such orbitals is very less. Energy of BMO is less, so it is more stable. Energy of ABMO is more, so it is less stable. Am I clear? Electron placed in BMO stabilizes a molecule because electron density in between the nucleus is more, attractive force is more. So BMO, if the electron is placed in bonding molecular orbital, it will increase the stability of the molecule. If the electron is placed in anti-bonding molecular orbital, it will destabilize the molecule. Am I clear, students? Let's move ahead. Let's see how the atomic orbital overlaps. Student, I am having two atomic orbital having wave functions psi A and psi B. BMO is formed when this psi A plus psi B, same phase combination, psi A plus psi B. Whereas ABMO is formed when psi A minus psi B. Basically destructive interference. And here we will have constructive interference. Now, just now we have discussed whenever a constructive interference occurs, the electron density in between the nucleus increases, attractive force increases, so stability will be more, potential energy will be less. So in case of bonding molecular orbital, the potential energy is less. Whereas in case of anti-bonding molecular orbital, internuclear repulsion increases because of the decreased electron density. And because of that, P is more. So on the energy diagram, BMO is placed at lower energy level, whereas ABMO is placed at higher energy level, right? Where will fill the electron first? According to Aufbau principle, electrons are always filled in the lower energy orbital and then subsequently in higher orbital. So first we will fill the electron in BMO and then in ABMO. Am I clear, students? Students, now let's see the representation of different types of molecular orbitals. And these molecular orbitals are formed by the linear combination of two atomic orbitals. Am I clear? Okay. Student, here z-axis is assumed to be internuclear axis. So the atomic orbitals are approaching along z-axis. This one is z-axis. Am I clear? Now, let's first of all talk about the linear combination of 1s atomic orbital. Student, 1s. It's having a spherical size, right? This one, sorry, shape, spherical shape. Spherical shape. Now, I'm having two 1s atomic orbitals. When two atomic orbital will combine, they will give us two molecular orbital. One bonding molecular orbital, one anti-bonding molecular orbital. When same phase combines, plus plus, right? It will lead to the addition psi A plus psi B. Constructive interference will have the formation of bonding molecular orbital, and that is 1s. They will undergo head-on overlap, and this head-on overlap will result in the formation of sigma bonding molecular orbital. So I will have this 1s same phase overlap results in the formation of sigma 1s bonding molecular orbital. Right, student? Here I am having nucleus of 1s, the nucleus of other 1s, and this is the representation of sigma 1s bonding molecular orbital. Now 1s positive combines with 1s negative. Subtraction, destructive interference. Student, here in between the nucleus, the electron density will be 0 because they are cancelling out each other. Subtraction, psi A minus psi B. So electron density in between the nucleus is 0. So I am going to get a nodal plane here. Am I clear, student? So when 1s positive combines with 1s negative will have destructive interference, which will lead to the formation of sigma 1s anti-bonding molecular orbital. We represent it like this: sigma star 1s. It's simply formed by the combination of positive 1s and negative 1s. Am I clear? And this is sigma star 1s, sigma star or sigma anti-bonding molecular orbital. Am I clear? In case of sigma anti-bonding molecular orbital, we'll have one nodal plane. Whereas in case of sigma bonding molecular orbital, sigma bonding 1s molecular orbital will have 0 nodal plane. Am I clear? Let's move ahead. 2s constructive will have the formation of this s orbital will always undergo head-on overlap. So I will have the formation of sigma bonding only. Now I can have sigma bonding, sigma anti-bonding. If plus minus combines, plus minus combine, I will have subtraction psi a minus psi b will lead to the formation of sigma star 2s. Once again, I will have one nodal plane here, nodal plane. Whereas in case of sigma 2s bonding molecular orbital will have 0 nodal plane. It's like this only. Am I clear? No nodal plane in sigma 2s, whereas one nodal plane in sigma star 2s. Now let's talk about the combination of p orbital. 2pz, 2pz. They are approaching along the internuclear axis. Head-on overlap results in the formation of sigma bonding, right? Now, if positive overlaps, what will happen? The electron density in between the nucleus will increase, right? So this is the nucleus of first and this is the nucleus of the second atomic orbital, and electron density has increased. This is sigma 2pz bonding molecular orbital. Now, plus combining with minus. So electron density in between the nucleus has decreased. So I'm going to get one nodal plane here. Student, am I clear? This is my nodal plane. I hope these things are crystal clear. Now, 2px lateral overlap. This lateral or sidewise overlap results in the formation of pi bond plus plus minus minus. If plus plus and minus minus will overlap, I will have constructive interference will result in the formation of pi bonding, that is pi 2px bonding molecular orbital. Student, now this plus plus, the electron density like this, minus minus, once again constructive electron density like this. In between, I will have a nodal plane. Am I clear? Now, if I talk about destructive interference, plus minus, minus plus, then I will have psi a minus psi b. Student, now along this axis also will have a nodal plane, and along this axis also, because along this axis also I'm having a destructive interference, and along this particular y-axis also and along x-axis also will have di, and in along both the axis I am going to get nodal plane, two nodal plane. And basically when this destructive interference occurs in 2px, I will have the formation of pi star 2px. Am I clear? Let's move ahead. Similarly, 2py, I will have pi 2py bonding molecular orbital getting formed and pi star 2py anti-bonding molecular orbital getting formed, similar to that of 2px overlap. Am I clear, student? Let's move ahead. Student, now the filling of electrons in these molecular orbital is really important, because lot of time you will be asked to compare bond energy, bond order, stability of molecule, and that you can simply compare by calculating bond order. And bond order is always calculated as number of bonding electrons minus number of anti-bonding electrons divided by 2. In order to calculate the number of bonding and anti-bonding electrons, you should know how to fill electrons in these molecular orbital. Students, electrons in molecules in two different order. One for a molecule having greater than 14 electrons will have a different order, and one for a molecule having less than or equals to 14 electron will have a different order. Let's see one by one. Student, for a molecule like oxygen, fluorine, what will be the total number of electron in oxygen molecule? 8 into 2, 16. So the total number of electron is greater than 14. In that case, we have the order like this. First, we fill the electron in sigma 1s, then sigma star 1s, that is sigma anti-bonding molecular orbital 1s, then sigma 2s, sigma star 2s. Okay, then we fill the electron in sigma 2pz. After filling electrons in sigma 2pz, we fill the electrons in pi 2px and pi 2py. They are degenerate. So first we will fill here equally. All the degenerates orbital are singly occupied, and then pairing will occur. Okay, then we'll fill the electron in pi star 2px equals to pi star 2py in the same order like this one, and then at the end we'll fill the electron in sigma star 2pz. Am I clear? For a molecule having number of electrons greater than 14, we are going to follow this order. Sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, then pi 2px equals to pi 2py, pi star 2px equals to pi star 2py, and then sigma star 2pz at the end. Am I clear? For the next one, for a molecules whose atomic number is less than or equals to 7, like for bromine, boron, carbon, nitrogen, for these molecules where the total number of electron is less than or equals to 14, we have the order. We follow this particular order. Sigma 1s will fill the electron first in sigma 1s, then sigma star 1s, then sigma 2s, then sigma star 2s, then we'll fill the electrons in pi 2px equals to pi 2py. Then we'll fill the electron in sigma 2pz. First we fill electrons in pi 2px equals to pi 2py. Then we fill electron in sigma 2pz. Then we fill the electron in pi star 2px equals to pi star 2py. And at the end we will fill the electron in sigma star 2pz. This is for a molecule having number of electrons less than equals to 14. For a molecule having electrons greater than 14. Am I clear, students? Let's move ahead. In a molecule having atomic number less than equals to 7, the energy of sigma 2pz orbital is higher. That's why we fill the electron first in pi 2px and pi 2py, and then we fill the electron in sigma 2pz, mainly in the molecules like boron, carbon, and nitrogen. Am I clear? Now, for the species having electrons greater than 14, this is the MO diagram. First, we fill the electron in sigma 1s, then we fill the electron in sigma star 1s, then sigma 2s, then we fill the electron in sigma star 2s, then we fill the electron in sigma 2pz, then we fill the electron pi 2px equals to pi 2py. You can see they are degenerates, and degenerates orbital are singly occupied first, and then only pairing will occur. So first we'll fill the electron singly, and then we'll do pairing. Then we'll have pi star 2px equals to pi star 2py, and at the end we will have sigma star 2pz. Am I clear, students? So this is the energy level diagram for a molecule having number of electrons greater than 14 for O2, for F2, for O2 plus, for O2 minus, for O2 2 plus. For all such molecule will follow this order. Am I clear? Next one. Energy level diagram for a molecule having number of electrons less than equals to 14. Student, here the order is sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. Then we will have pi 2px. Student, here we'll have first we'll have pi 2px. This is wrong. Pi 2px, pi 2px equals to pi 2py. Then we'll have sigma 2pz, and then we'll have pi star 2px equals to pi star 2py, and at the end we'll have sigma star 2pz. It's mainly applicable for the molecule like B2, C2, N2, N2 plus, N2 minus. Even you will say, sir, the number of electron is greater than 14. In case of N2 minus, the number of electron is 15. Now you will tell, sir, we should follow that particular order. No. We'll always look at the parent molecule and we'll check the number of electron in parent molecule. Here the parent molecule is nitrogen, which is having 14 electrons. So even for N2 minus, we'll follow this order only. Am I clear? Let's move ahead. Students, now this bond order calculation. It represents the number of bonds between two atoms. A bonded to B. How many bonds is there? How many bond? 1. So what will be the bond order? Bond order equals to 1. A doubly bonded to B. How many bonds connecting A and B? 2. So what is the bond order? Bond order equals to 2. Right? Student, if we have to calculate bond order is always equals to half into number of electrons present in BMO, that is bonding molecular orbital, minus number of electrons present in anti-bonding molecular orbital. Half number of electrons present in BMO minus number of electrons present in ABMO. Am I clear? NB represents the total number of bonding electrons. Na represents total number of anti-bonding electrons. NB minus Na upon 2 represents bond order. Student, if NB is greater than Na, molecule will exist. If NB is less than Na, bond order will be negative, molecule won't exist. Even NB, this one is not feasible. NB less than Na not feasible. If NB equals to Na, in that case bond order will be 0 and molecule will not exist. Am I clear? Let's move ahead. Student, now this application of bond order, this is really important. Okay, let's have a look at this. Student, this bond order is directly proportional to bond strength, or we say bond energy. Higher is the bond order, higher will be the bond energy, and lesser will be the bond length. Bond order directly proportional to bond strength, directly proportional to bond energy, directly proportional to stability of the molecule, inversely proportional to bond length. Am I clear? In case of fluorine molecule, the bond order is 1. In case of oxygen molecule, the bond order is 2. In case of nitrogen, the bond order is 3. With increase in the bond order, the bond strength will be more. So N2 will have higher bond energy as compared to O2. O2 will have higher bond energy as compared to F2. If I have to compare the bond length in FF will be more as compared to the bond length of OO, which will be more as compared to the bond length of NN. Am I clear? With increase in the bond order, the molecules come closer, the bond length decreases. Student, through this MOT, we can also comment on the magnetic behavior of a molecule. If a certain molecule is having unpaired electron in its MO in their MO configuration, like oxygen, it is having unpaired electron in its MO configuration. That's why O2 molecule, even diatomic, it's paramagnetic in nature. Let's see. Oxygen, O2 molecule. Total number of electrons, 16 electrons. Let's fill MO for this one. 1 is sigma, 1 is 2, sigma star 1 is 2, sigma 2 is 2, sigma star 2 is 2. Total number of electrons that we have filled is 8. Then we'll have sigma 2pz, p orbital, Any orbital will occupy maximum of 2 electrons. I will fill 2 electron, 10 electrons. Now I have pi 2px equals to pi 2py, 2 and 2. So till yet we have filled 14 electrons. Now pi star 2px equals to pi star 2py. Student, now I have 2 electrons only left and these 2 orbitals are degenerate. So I'll fill 1 electron here and 1 electron here. So student, now if I look at this particular MO configuration, pi star is having 1 electron. It's having unpaired electron. Pi star 2px is having 1 electron. Pi star 2py is having 1 electron. So in case of O2 molecule, its MO configuration is having unpaired electron. That's why O2 molecule is paramagnetic in nature. It will get attracted in the magnetic field, right? When electrons in MO are unpaired, molecule will be paramagnetic. When electrons in MO are paired, molecule will be diamagnetic. Am I clear, students? Please copy all these things. For isoelectronic molecular species, the value of bond order and magnetic moment generally remains the same. Yeah, because the number of electrons is same, right? So for isoelectronic species in general, not always, in general, the bond order and the magnetic behavior is same. Students, now I have formed a table for different electrons and then I have calculated the bond order, the magnetic behavior, each and everything. So please go through this table carefully. If the number of electrons in a molecule is 10, in which molecule the number of electrons may be 10? In case of boron molecule, B2. So the molecule is B2, right? The number of electrons is 10. In that case, the bond order is 1. How? Let's see. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Then we'll have pi 2px1 equals to pi 2py1. 2 minus 2, 2 minus 2. Till yet they cancel out. Number of bonding electrons 2, 4, 6. Number of anti-bonding 4. 6 minus 4 divided by 2. Bond order 1. Now, if I look at the magnetic behavior, the MO configuration is having unpaired electrons. So this B2 molecule is paramagnetic, right? Let's suppose B2 minus or C2 plus. If for these molecules, the number of electron is 11. In that case, the bond order will be 1.5. How? Let's see. Because here I'm going to put one more electron. Till yet I have filled 10 electrons. Now I need to fill 11 electrons. So I'll fill one more electron here. 2 here, 1 here. Am I clear? Now the number of bonding electron will be 7. Anti-bonding 4. 7 minus 4, 3 divided by 2. Bond order 1.5. Still molecule paramagnetic. Unpaired electron. Now for C2 molecule. Here also now this 2 pi y1. Here also I will have 2 electrons. So what will be the bond order? 8 minus 4 divided by 2. 4 divided by 2. Bond order will be 2. Now if I look at the magnetic behavior, the MO configuration, if I look at this MO configuration, all the orbitals, the electrons in these orbitals are completely paired. So this C2 molecule is diamagnetic in nature. Diamagnetic. Am I clear? Bond order in case of C2 molecule is 2. One more important point. Student, basically in case of C2 molecule, both these bonds are pi bonds. Because sigma electrons, they cancel out each other. Number of sigma bonding electrons equals to the number of sigma anti-bonding electrons. So only pi bonding electron is there. So in C2 molecule, both these bonds are pi bond. Am I clear? Next one. In case of N2 plus C2 minus, number of electron is 13. In that case, bond order will be 2.5. Now students will have electron entering into sigma 2pz 1, right? So number of bonding electrons 8. Anti-bonding, sorry, number of bonding electrons 9. Anti-bonding 4. 9 minus 4 divided by 2, 2.5. Molecule paramagnetic 2pz1, right? So C2, sorry, C2 minus N2 plus, these molecules are paramagnetic. Next one, N2, completely N2 molecule. Student, the bond order is exactly 3 because now I will have sigma 2pz2. So 10 bonding electrons, 4 anti-bonding electrons, bond order 10 minus 4 divided by 2, 6 by 2, it's 3. Bond order 3, molecule diamagnetic. Next one, N2 minus or O2 plus. Student, although for O2 plus will have a different configuration, N2 minus 15 electrons, right? Student, here the bond order is once again 2.5 because now the electron will enter into anti-bonding molecular orbital. 10 bonding, 5 anti-bonding, 10 minus 5 divided by 2. Still 1 electron in the anti-bonding molecular orbital. Molecule is paramagnetic. O2, 16 electrons. Just now I have done it. Bond order 2, molecule is paramagnetic because 1 electron in pi star 2px and pi star 2px now will get added. I will have pi star 2px equals to 1, pi star 2py equals to 1. So 1 electron is in pi star 2px and pi star 2py in case of oxygen molecule. So it's a paramagnetic. Next, O2 minus. The bond order is 1.5. 2 electrons here, 1 electron here. Am I clear? So 10 bonding, 7 anti-bonding, 10 minus 7 divided by 2. Molecule still paramagnetic. 18. Fluorine molecule. 2 and 2 here, students. So 10 minus 8 divided by 2. Bond order 1. Molecule, all the molecular orbitals are completely paired up. So molecule is diamagnetic. Fluorine molecule, diamagnetic. So basically, through this table, I have calculated the bond order of n different number of molecules. Please go through this table carefully. It will save a lot of your time during examination. Write electronic configuration of O2 and explain its paramagnetic behavior. Just now we have seen it, right? O2 is paramagnetic. Bond order 2. Number of bonding electrons 10. Anti-bonding 6. 10 minus 6 divided by 2. Right? Same. Yeah. Compare the bond length, bond order, bond strength of O2, O2 minus and O2 2 minus. O2 bond order is 2, right? Just now we have done it. O2 minus 17, bond order 1.5. O2 2 minus, bond order 1. More is the bond order, more is the bond strength, more is the stability, more is the bond energy. So student, if I have to compare the bond order and the bond strength, in case of O2 it's max, then O2 minus, then O2 2 minus, bond order 1, 1.5, and here 2. Bond order inversely proportional to bond length. So in case of O2 2 minus, the bond length will be maximum. Single bond character, here 1.5, and here double bond character, bond length will be less. With increase in bond order, the bond length decreases. Which of the following molecules have only pi bond? Just now we have done this one. C2 molecule, both the bonds are pi bond only. And now we have one more important concept left related to this molecular orbital theory. And that particular concept says, if the two molecules have same bond order, then molecules having lesser number of electrons present in ABMO will be more stable. Let's try to understand this with one example. We have to compare the stability of N2, N2 plus, N2 minus. 14 electrons, bond order 3. How much? 13 electrons, bond order 2.5. 15 electrons. Bond order once again 2.5. No doubt in case of N2 the bond order is 3. But in case of N2 plus and N2 minus, the bond order is same. Now we need to check the number of anti-bonding electrons. Student, in case of N2 minus, the number of anti-bonding electron is more. Student, here we have 10 minus 5 upon 2 and the bond order is 2.5. 10. Whereas in case of N2 plus, we have 9 bonding electron, 4 anti-bonding electron by 2. Number of anti-bonding electron is less in case of N2 plus as compared to N2 minus. So which one will be more stable? N2 plus will be more stable as compared to N2 minus. The stability order will be like this: N2, then N2 plus, and then N2 minus. With this, the molecular orbital theory comes to an end. Students, now let's discuss the next type of covalent bonding, and the next covalent bonding that we are going to discuss is there on the screen, and it's coordinate covalent bond, or we also say it as dative bond. Student, this dative bond is formed between a Lewis base and a Lewis acid. What do we mean by the term Lewis base? All the electron rich species, the anionic species, the species containing pair of electrons, unshared pair of electrons, such species are electron rich species and they are Lewis base. Lewis acids, they are the electron deficient species, species having vacant orbital, species having incomplete octet, or all the cationic species, they are the electron deficient species, so they are Lewis acid. A coordinate covalent bond is formed between a Lewis base and a Lewis acid. Just like covalent bonding, here also the bond is formed by the sharing of electrons, but there is no equal sharing unlike covalent bond. Here the sharing of one of the atoms or one of the species acts as a donor and the other one simply accepts it. Obviously the donor one will be the electron rich species. So students, here electron is donated from Lewis base to a Lewis acid. Am I clear? Let's have a look. Unlike covalent bond, it is formed by the unequal contribution of electrons. Shared electron pair is contributed by one atom only, donor, that is Lewis base. Okay, other atom only provides vacant orbital. It acts as a acceptor. It simply provides its vacant orbital and accept a pair of electrons. Now, necessary condition is that one atom should have lone pair, one atom should be electron rich, and the other should have a vacant orbital. X is donor and Y is the acceptor. And if Y is acceptor, it should have a vacant orbital, and X should have a pair of electrons at least to donate. Am I clear? As we can see here, NS3, this nitrogen is having unshared pair of electrons, and BF3, this boron, is having a vacant 2p orbital. So lone pair is donated from this nitrogen to vacant p orbital of boron. A bond is formed between nitrogen and boron. Basically, student, such bonds are represented by arrow, and the sign of arrow, or basically this direction of arrow, is from donor to acceptor side. Am I clear, students? Okay. We can see here this H plus is an electron deficient species, right? It simply accepts electron, a pair of electron from ammonia, and a coordinate covalent bond is formed between NH3 and H plus. And this is how NH4 plus molecule is formed. Same story here also. F minus electron rich species, BF3 electron deficient species. A coordinate covalent bond is formed from a Lewis base to a Lewis acid. The direction is from electron rich to electron deficient species, right? N2O, same story. Friends, I hope you have understood this coordinate covalent bonding also. Let's move ahead, and now it's time to discuss the different types of force operating in a covalently bonded molecule. The next topic which I am going to discuss is the different types of intermolecular forces. Let's discuss one by one. The first intermolecular force that we are going to discuss is iron dipole force. Where this force is applicable, it is mainly applicable where one of the molecule is in ionic state. The force operating between a ion and a polar molecule. Force operating between a ion and a polar molecule is referred as ion dipole force. M plus water. The force operating between this cation and the water molecule is ion dipole force. Right, student? Let's try to understand this one. M plus O, del negative, H and H. H del positive, del positive. Now between the positive and this del negative, one force of attraction will be operative, and this force of attraction is ion dipole. So the force operating between, or the intermolecular force operating between an ion, maybe cation, maybe ion, and a polar molecule is ion dipole force. Am I clear? Na plus water, I can have even Cl minus and water. This one will also get solvated, right? Cl minus H, O, H, H delta positive, Cl negative, one force will be applicable. And this particular intermolecular force, this particular bonding between this H and Cl is ion dipole bonding. It's a physical bonding. Am I clear? Next one, ion induced dipole force. Such type of intermolecular force is operating between a ion and a non-polar molecule. Ion and a non-polar molecule. Whenever a non-polar molecule comes into the field of ion, basically it also gets polarized due to induction. And then the intermolecular force operating between this ion and the non-polar molecule is ion induced dipole force. Am I clear? Like I minus and I2. This I2 is non-polar, whereas I minus is in ionic state. The intermolecular force operating is ion and non-polar, and it's ion induced dipole force. Am I clear? Next one. Dipole. Such intermolecular force is mainly applicable between two polar molecule. Between two dipoles, the force of attraction operating is dipole. It's also referred as Keesom force. Am I clear? Between two polar molecule, HCl, H2O, HCl, H2O. H2O is also polar, HCl is also polar. The intermolecular force of attraction operating between these two covalently bonded molecules is dipole. NH3 polar molecule, H2O polar molecule. The intermolecular force of attraction operating between these two polar molecules is dipole. Am I clear? Dipole induced dipole. The intermolecular force of attraction operating between a polar and a non-polar molecule. Polar and non-polar molecule. Polar. Right? Let's see the example. HCl and Cl2. HCl is polar, Cl2 non-polar. The intermolecular force operating between this polar and non-polar is dipole induced dipole. In the presence of this polar molecule, even the Cl2 also gets partially polarized due to induction, and then the force of attraction operating between these two molecules, that is HCl and Cl2, is polar induced dipole, and we say this force as Debye force. So we have Keesom force, dipole induced dipole is Debye force. Am I clear, students? Okay. Instantaneous dipole induced dipole, the most important one, or we say it as London force. Such intermolecular force of attraction is mainly applicable between two non-polar molecules. Between two non-polar molecules, this London force is always applicable. That's why we say it instantaneous dipole induced dipole. Whenever the two non-polar molecule comes in close contact with each other, as they try to approach towards each other, they get partially polarized due to induction. Instantaneous polarization occurs, and we say it as instantaneous dipole induced dipole. Am I clear? between two non-polar molecule. Cl2, Cl2, xenon, xenon, hydrogen, hydrogen, all these molecules are non-polar. So between two non-polar molecule, this London force is applicable. Is this clear, students? Let's move ahead. Student, if I talk about the order of strength, the most strongest force is dipole-dipole, then dipole-induced dipole, and then induced dipole-induced dipole. Am I clear? So Keeson force is the strongest one between polar-polar, polar-polar stronger, then polar, non-polar, non-polar, and then the least one is non-polar, 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 non-polar. Am I clear? I hope these things are crystal clear. Identify the type of weak force operating between the following pair of species. HCl, HCl, Keeson force, dipole, dipole, right? H2S, H2S. H2S is also a polar molecule. H2S is also a polar molecule. It's a Keeson force only. Am I clear? HCl and Cl2. Cl2 non-polar. HCl polar. Polar, non-polar. Dipole induced dipole. It's a Debye force. H2O polar. CCl4 non-polar. Non-polar. Polar, non-polar, Debye force. Polar, polar, Keeson force. Am I clear? Non-polar, non-polar, London force. Are these things crystal clear to you all? Shall I move ahead? Let's move ahead. Xenon, water, non-polar, polar, Debye. Dipole induced dipole. Non-polar, non-polar, London force. NS3, NS3, polar, polar, Keeson force, dipole, dipole. Dipole, dipole. Am I clear? Cl minus H2O. Cl minus is a ion. H2O polar molecule. Ion dipole. Ion dipole. Br minus Br2. Ion non-polar. Ion induced dipole. Ion induced dipole. Next one. He, He. Between two non-polar molecules, the intermolecular force of attraction which is operating is London force. London force. Am I clear, students? Please copy it. In general, we have studied the comparison. Keeson is the strongest one, then we have Debye, and then we have London force. But if I have to compare the order of London force operating between two non-polar molecules, then London force simply depends on molecular weight, directly proportional to molecular weight of a compound. Higher is the molecular weight, higher will be the London force. Am I clear? One more important point. If the molecular weight of two compounds is same, in case of isomers, the molecular formula is same, right? So in that case, molecular weight will be same. If the molecular weight of two non-polar molecules is same, then check the surface area. Larger the surface area, larger will be the London force. If the magnitude of molecular weight is same, then criteria number 2, check surface area. Surface area. More is the surface area, more is the London force, more is the intermolecular force of attraction, stronger will be the physical bond. Am I clear, students? So as I move from helium to neon to argon to krypton to xenon, what's happening here? Molecular weight is increasing. With increase in the molecular weight, the intermolecular force of attraction which is operating is London force. This magnitude of London force will increase. Molecule will come closer. Liquefaction will become Eg. Am I clear, student? Liquefaction Eg. Solubility in water will increase because the molecules will come closer, right? The boiling point also depends on intermolecular force of attraction. Stronger the intermolecular force of attraction, higher will be the boiling point, and even sometimes this melting point also depends on intermolecular force of attraction. In general, melting point depends on crystal lattice energy for ionic compounds, but here we can say this melting point also depends on IMF, intermolecular force of attraction. Is this clear? Shall I move ahead? Let's move ahead. Moving ahead, the next topic that we are going to discuss is once again one of the most important topic of chemistry, and it's hydrogen bonding. Student, if I talk about this hydrogen bonding, it's a special case of dipole-dipole interaction or Keesham force. Now, when this dipole-dipole interaction is applicable, when we have two polar covalently bonded molecule, right? Student, here also we need two polar covalently bonded molecule. Two polar molecule we need. Molecule. Now, the molecule number 1, so let's suppose it's M1. It has to be polar, and then it should contain acidic hydrogen. Acidic hydrogen. What do we mean by the term acidic hydrogen? Hydrogen connected to a highly electronegative elements like nitrogen, oxygen, and fluorine. First polar molecule or one of the polar molecules would contain acidic hydrogen, and second polar molecule M2 should contain an atom that should have lone pair. M2 should have a lone pair, should have pair of electrons of non-bonding electrons or pair of a lone pair. Am I clear? Okay. Now let's try to understand. Student, I am going to take a molecule HF, right? HF. Is the hydrogen connected to highly electronegative element? Yes. Is HF molecule a polar molecule? Yes, it's a polar molecule also. And here this hydrogen is acidic because fluorine is highly electronegative, so it will have a del positive, right student? Now I am going to take one more molecule, H2O. OHH. Is this molecule have a lone pair? Yes. Water, oxygen is having a lone pair. Now student, OHH. O having lone pair, having del negative, this hydrogen having a del positive. Between this del positive and this lone pair, a physical bond is formed, right? And this particular physical bond is nothing but H bond. Am I clear? So for hydrogen bonding, there is only one condition. H bonded to an element X. This H should be bonded to element X, and this element X should be either NOF. The second polar molecule should have an element Y, and this Y should have lone pair, and this Y should also be one of these following atoms. Either it has to be fluorine, oxygen, nitrogen, and chlorine. Then between this H and this Y, a physical bond is formed, and this particular physical bond is H bond. Am I clear, student? Now, the strength of this particular H bond will depend on acidic strength of this H plus. Higher is the acidic strength, higher is the delta positive on this H plus, more will be the strength of hydrogen bonding. Higher the acidic strength, more will be the strength of hydrogen bonding. Now, how the acidic strength will increase? Higher the electronegative elements connected to it. Stronger the electronegative element connected to it, more will be the delta positive on it, stronger will be the H bond. Condition number 1, this H should have more delta positive, means highly electronegative elements should be attached to this hydrogen. Condition number 2, more charge density, more electron density should be there on this Y. Stronger the electron density on Y, stronger the electron density, more is the electron density on Y, better will be the donation ability, stronger will be the H bond. Am I clear? So this Y should be more electron rich and this H should be more electron deficient. H should be more electron deficient. And how can you increase the electron deficiency of this H? By connecting it to a more electronegative element. And this Y should be highly electron rich. Then the hydrogen bonding will be a stronger one. Am I clear? Okay. Yeah. So student, we can see here HF, HF. This H is having delta positive, this fluorine is having electron density, a physical bond is formed, and this physical bond is H bond. The energy released in this process is 10 kilocalorie per mole. Whereas if I talk about this one, OH, H delta positive, oxygen is having a donation ability. Here also I am having this bond is also a H bond. But now you can see the energy released is 7 kilocalorie per mole. Why the energy released is less? Because the delta H positive on this oxygen is less. In case of fluorine, the electronegativity is more, so electron deficiency is more here. Delta acidic strength of this hydrogen is more. More is the acidic strength of hydrogen, stronger will be the hydrogen bonding, larger will be the amount of energy released. You can see here in case of ammonia, nitrogen is not that electronegative as compared to oxygen and fluorine, right? Even though this nitrogen is having a better donation ability, but delta positive is less delta positive, lesser the strength of H bonding. Am I clear, students? Shall I move ahead? Let's move ahead. Order of strength of H bonding. Student, already we have seen this. Strength of H bonding simply depends on first acidic strength of hydrogen. Can I say in this particular case, acidic strength will be maximum. So H bonding strength will be more in this one. H positive, F del negative. This bond is H bond. Now where you find more acidic strength? Here, because rest, and here also. Now student, if I have to compare between D and E, in both the case, delta positive on hydrogen is same because both these compounds are connected to oxygen. Right, here also hydrogen is connected to oxygen, and here also this hydrogen is connected to oxygen, so the magnitude of delta positive is same. Now the strength of hydrogen bonding will depend on electron donation ability. Nitrogen is having a better electron donation ability as compared to oxygen. Am I clear? So can I say in this case the strength of H bonding will be more. So after A I will have E. Right, after E, D, right? First, always give preference to acidic strength of hydrogen, second preference donation ability. Now between B and C, now acidic strength is same, more is the donation ability, better will be the strength. So C will have more donation ability than B. This is the order of a strength of H bonding. This particular concept is really important. VVI. Am I clear, student? Shall I move ahead? Okay. If I talk about the types of hydrogen bonding, we have two types of hydrogen bonding observed. One, intermolecular hydrogen bonding. Second one, intra. Name itself says hydrogen bonding observed in a single molecule. Intra, within the same molecule, between two different molecules, intermolecular, between two different polar molecule. This intramolecular H bonding is observed in the same molecule. We'll discuss one by one. Student, till yet mainly we were talking about this intermolecular hydrogen bonding only. HF. You can see, right? A long polymeric chain is there. H, F. This H is having delta positive, F lone pair. A physical bond is formed. This bond is H bond. Once again, this HF molecule is also connected to this HF molecule via H bond. This bond is H bond. Why? Because H is having delta positive, fluorine having electron density, del negative, del H bond, H bond, H bond, H bond. Am I clear, student? Similarly here also, this hydrogen connected to nitrogen is acidic, delta positive. Nitrogen having electron density, lone pair, delta positive lone pair. Am I clear? I hope these things are crystal clear to you. All these are the examples of intermolecular H bond, the hydrogen bond found between two different polar molecules, right? Student, if I talk about the application of intermolecular hydrogen bonding, the best one is the structure of ice. Student, this ice is having an open case like structure. And if someone asks you what's the hybridization here of this one water molecule, basically it is sp3. If someone asks you one water molecule is surrounded by how many water molecule through H bond in ice, student, you can see here. Let's focus on this particular water molecule. If you see this on this water molecule, it's surrounded by how many water molecule? Through H bonding. It's basically physically bonded through 4 water molecule. 1, 2, 3, 4. Right? 4 particular water molecule is physically bonded to 1 water molecule. So it's having a tetrahedral structure. Tetrahedral structure. If someone asks you the coordination number of water molecules surrounding a particular water molecule in the structure of ice, it's 4. 4 water molecule is physically bonded to one water molecule through intermolecular H bonding. Am I clear? Ice has an open case like a structure due to which the distance between water molecule increases, hence the volume decreases. If volume will decrease, density will be less, and this is the region. This ice is having less density as compared to water, and it floats on the surface of water. Am I clear? Let's move ahead. Boric acid, it's also having a seat like a structure. Then we have studied in organic chemistry, whenever we have an acidic acid, it readily dimerizes, right? It undergoes dimerization, and this dimerization occurs via intermolecular H bond. You can see here acetic acid CH3 C double bond O OH, right? OH. Now this is one of my acetic acid molecule. This one is the another one, right? This H is having a delta positive. This oxygen is having electron density lone pair. Between this H and oxygen doubly bonded O, we will have H bonding. Similarly, between this hydrogen delta positive and this doubly bonded oxygen, we will have a physical bonding, and it's H bonding. Am I clear, student? Let's move ahead. All these are the examples of hydrogen bonding. You can easily note down all these examples. Students, now let's focus on intramolecular hydrogen bonding. If I talk about this intramolecular hydrogen bonding, such H bonding is operating within a single molecule. The best example is orthonitrophenol, having a structure like this: OH N doubly bonded O. Student, if I look at this particular structure, can I say this particular hydrogen, this one, is acidic in nature as it is bonded to oxygen atom, a highly electronegative atom? So I will have delta positive. Is this oxygen having lone pair? Yes, I will have delta negative. Now between this hydrogen and oxygen, one physical bond is operating, and this physical bond is H bond. Now since this H bond is operating in a single molecule within the molecule, we see it as intramolecular hydrogen bond. Am I clear? If hydrogen bonding is operating within a molecule, we say it as intramolecular hydrogen bond. Let's take one more example. This one, OH salicylic aldehyde, OH C double bond OH. Is this hydrogen acidic? Yes. Why it is acidic? Because it is connected to more electronegative element. So it will have a delta positive. Is there any lone pair present on this oxygen? Yes. So there is delta negative here. Now between this delta positive and delta negative, we will have a physical bond, and this physical bond is your intramolecular H bond. Right, student? I hope you understood this intramolecular H bond. All these are the examples of intramolecular H bond. Now, it's time to discuss the application of this hydrogen bonding. And this particular application is once again really important. VVI. You can simply mark it as VVI. Student, with increase in the extent of hydrogen bonding, solubility increases. This point is really important. Next one. Hydrogen bonding. With increase in the extent of hydrogen bonding is nothing but an intermolecular force. And if the magnitude of intermolecular force will increase, polarity will increase, and with that the boiling point will increase. So can I say if hydrogen bonding is more in a molecule, the melting point will be more, the boiling point will be more, viscosity will be more, right? Fluidity will be less, the mobility will be less. So viscosity will be more, surface tension will be more. Students, now let's summarize the application of this intermolecular hydrogen bonding. Student, if the extent of intermolecular hydrogen bonding increases, then solubility increases. More is the extent of intermolecular hydrogen bonding, higher will be the solubility. If the extent of intermolecular H bonding is more, then polarity is more. More is the polarity, higher is the boiling point, higher is the melting point. More is the extent of intermolecular hydrogen bonding, more will be the viscosity, lesser will be the fluidity, lesser will be the tendency to change the state. So lesser will be the volatility, lesser is the volatility, lesser will be the vapor pressure, more will be the surface tension. Am I clear? Friends, now let's study the difference between the intermolecular hydrogen bonding and intramolecular hydrogen bonding. What will happen to a particular molecule if it's having intramolecular H bonding, and what will be the impact if a certain molecule is having intermolecular hydrogen bonding? Student, basically both these this H bonding is itself a excellent application of Kisam force. So in both the case, dipole-dipole interaction is there. Now, in case of this intramolecular hydrogen bonding, there is a ring formation, right? Association is occurring within the molecule itself. Because of ring formation, the association is occurring within the molecule itself, right? Now, what will happen? The surface area will decrease. And if surface area will decrease, obviously the magnitude of Vander Wall force will decrease, right? In that case, what will happen? The boiling point will be less. So student, if in the molecule intramolecular H bonding is observed, in that case boiling point is less, volatility is more. Am I clear? So whenever you see a molecule showing intramolecular H bond, in that case the boiling point is going to be less as compared to the molecule exhibiting intermolecular H bonding, because in intermolecular H bonding we have a strong association of molecules. The surface area is increasing. With increase in the surface area, the magnitude of Vander Wall force increases. With increase in the magnitude of Vander Wall force, polarity increases, boiling point increases. So which one will have more boiling point? Orthonitrophenol and paranitrophenol. Where? In this case of paranitrophenol, the boiling point will be more. Which one is steam volatile? Orthonitrophenol will be steam volatile. It is highly volatile, right? The boiling point is less. BP less. Even solubility will be less. If intramolecular H bonding is present, solubility will be less. Solubility less, right? In case of intermolecular hydrogen bonding, solubility is very high, more is the extent of intermolecular H bonding, higher is the solubility, higher is the boiling point, lesser is the volatility, higher is the viscosity. In this case, in case of intramolecular H bonding, this viscosity is also less. Am I clear, student? Student, this was all about the different types of intermolecular force of attraction. I hope these things are crystal clear to you all. Students, moving to the next type of bonding that we have to study is electrovalent bonding or ionic bonding. The name itself says ionic bonds. So it is basically formed between two ions, a cation and a anion. So basically ionic bond is simply formed between an electropositive element and a electronegative element. And in general, metals are electropositive, whereas non-metal have a tendency to accept electron. They have a tendency to gain electron, so they are electronegative in nature. So if I say ionic bond is the bond formed between a metal and a non-metal, is this statement correct? Yes. Basically, in such type of bonding, there is a transfer of electrons from electropositive element to a electronegative element. Unlike covalent bonding, here we don't have sharing of electron. Here we have a complete transfer of electron from a electropositive element to a electronegative element. Am I clear, student? Let's have a look here. It is the electrostatic force of attraction operating between a cation and a anion. Cations are positively charged, anions are negative charged. Between opposite charged particles, the force of attraction which is operating is electrostatic or Coulombic force of attraction, right? So in case of ionic bonding, the intermolecular force of attraction which is operating is Coulombic force, or you will say it as electrostatic force of attraction. Am I clear? Okay. The chemical bond formed between two or more atoms as a result of complete transfer of one or more electrons from one atom to another is called ionic bond or electrovalent bond. Basically, ionic bond is formed by the complete transfer of electron from one atom, from the electropositive atom to a electronegative atom. Am I clear, students? Let's have a look at some of the examples. MgO, magnesium, metal, it will have a tendency to lose electron. It will have a tendency to lose its valence shell electron, right? Now, we just like covalency, here also we need to define one very important parameter, and that is electrovalency. What do we mean by the term electrovalency? It's simply the number of electrons lost or gained by a particular element. The number of electrons lost or gained by a particular element. If I talk about magnesium, the valency is 2, right? So in any bond formation, it is going to lose 2 electrons. So what is the electrovalency of magnesium? 2. If I talk about oxygen, what will be the electrovalency? 2. Chlorine, 1. Calcium, 2. Am I clear, student? So the electrovalency of calcium is going to be 2. Electrovalency of chlorine is going to be 1. It's basically the valency. Electrovalency, you can simply say it as valency. Am I clear, student? Okay. So MgO, in the formation of this MgO, there is a complete transfer of electron from magnesium to oxygen. Magnesium loses 2 electrons, whereas oxygen accepts 2 electrons. As soon as this magnesium loses 2 electrons, it will form Mg2 plus ion in the gaseous state, right? If oxygen is accepting 2 electrons, it is going to form O2 minus gas. Now, ionic bond is the bond formed between this cation and the anion, MgO. When this Mg2 plus gas will combine with O2 minus gas, will have the formation of MgO solid. If I talk about the nature of bonding in this MgO solid, it's nothing but ionic bonding. Am I clear, student? NaCl. Sodium loses one electron, form Na plus gas. Chlorine accepts one electron, it forms Cl minus gas. Now this Na plus and Cl minus will combine, and the nature of bonding will be ionic bonding. Is this crystal clear now? Shall I move ahead? Let's move ahead. Now let's discuss the physical properties of the compounds where we have ionic bonding. Student, if I talk about the physical state itself, first of all, in ionic bond, what is the intermolecular force of attraction operating? It's electrostatic force of attraction. And can I say, since electrostatic force of attraction is operating between the oppositively charged ions, so the intermolecular force of attraction will be very, very strong. So the molecules will be closely packed. Am I clear, student? And if the molecules are closely packed, they are going to be hard, they are going to be much denser, they are going to be much brittle, because the intermolecular force of attraction which is operating in ionic bonding is a very strong intermolecular force of attraction, and that is Coulombic force of attraction. Since the attractive force is much dominant, the molecules are closely packed, and if it's closely packed, obviously density is going to be more, obviously the brittleness is going to be more, obviously the hardness will be more. Am I clear, student? They are even brittle in nature. Okay. One more term, isomorphism. What do we mean by this term isomorphism? The compounds having the same number of electrons and have similar configuration of cations and anions. Such conditions are referred as isomorphism. Am I clear? FeSO4.7H2O isomorphous with MgSO4.7H2O, right? Because similar type of a structural arrangement is there. Am I clear, student? Okay, let's have a look. Na plus 10 electrons, F minus 10 electrons, Mg2 plus 10 electrons, O2 minus 10 electrons. They are basically isoelectronics. Right? Now if I talk about their electronic arrangement, electronic configuration, same 2-8, 2-8, 2-8, 2-8. Am I clear, students? I hope these things are crystal clear. Shall I move ahead? Let's move ahead. Ca2 plus 288, Cl minus 288, K plus 288, S2 minus 288, P3 minus 288. Am I clear? All of them have the similar number of electrons, they have the similar electronic configuration. Such a pairs are referred as isomorphic pair. Am I clear now? Let's move ahead. Student, if I talk about this boiling point and melting point, boiling point also simply depends on intermolecular force of attraction. If the intermolecular force of attraction is more, obviously boiling point is going to be more. In case of ionic solids, there is a strong Coulombic force of attraction. There is a strong Coulombic force of attraction. Because of that, the molecules are closely packed. It's tough to break the bond. Obviously, the lattice energy is going to be more. We will talk about this lattice energy. And if the molecules are closely packed, it's tough to break the molecule, right? So even the melting point will also be higher. Boiling points depends on intermolecular force of attraction, whereas melting point depends on packing. Ionic solids are closely packed, so they have higher melting point, they have higher boiling point because of high intermolecular force of attraction. Am I clear? Ionic compounds have high boiling point and high melting point. Why high boiling point? Because of a strong intermolecular force of attraction. Why high melting point? Because of closed packing, closed packed. Right? And what's the driving? What's the main reason for these things? The strong electrostatic force of attraction between oppositively charged ions, between a cation and a anion. Am I clear, student? Let's move ahead. Next, conductivity. In solid state, ionic compounds do not conduct. Why? Because they don't contain any free electrons, right? As soon as they get converted into molten state or they are dissolved in water, now they are in aqueous state. In aqueous state, they contains loosely held electrons, they contains free electrons, and these free electrons make them a good conductor. Am I clear, students? If I talk about solubility, generally more soluble in polar solvents. Ionic compounds, they are completely polar in nature, like dissolves like. So ionic compounds are mostly soluble in water because water is a polar solvent. Polar solvent, like dissolves like. Less soluble in non-polar solvent like benzene, CCl4, N-hexane. Ionic compounds are mostly insoluble in non-polar solvents. They are highly soluble in polar solvents. Am I clear? Shall I move ahead? Let's move ahead. Student, moving ahead, just now I had used the word lattice energy. While I was talking about this melting point, I told this melting point depends on lattice energy. Now it's time to understand what do we mean by the term lattice energy. Let us try to understand. Student, you might have heard about this particular compound, NaCl solid. Have you heard about this? NaCl solid, rock salt structure. Rock salt structure, right? In solid state, class 12 student have studied it, right? For class 11 student, now let's try to understand how it is formed. This NaCl is an ionic compound, right? Because it's containing one metal and non-metal. And electrovalent compounds or ionic compound contain one electropositive elements and one electronegative element, metal and non-metal. The compound formed between a metal and non-metals are generally ionic compounds, right? Now, when this Na plus gas, Na plus in the gaseous state will combine with Cl minus in the gaseous state, they are going to form NaCl solid. The amount of energy released in this process when these ionic compounds gets converted to a pure solid NaCl, when these ions, charged ions, gets converted to a neutral species NaCl, the amount of energy released in this process is nothing but lattice energy. Am I clear, student? When this Na plus gas combines with Cl minus gas, they result in the formation of NaCl solid. And in this process, in this chemical reaction, the amount of energy released is referred as lattice energy. Let's try to understand this definition. The amount of energy released when a gaseous cation and anions are combined to form 1 mole. It's always defined per mole of ionic solid. The amount of energy released in this formation of 1 mole of ionic solid is nothing but lattice energy. Am I clear, students? Okay. If I talk about this lattice energy, it simply depends on 2 factors. First, charge factor. Higher is the charge, higher is going to be the electrostatic force of attraction, and stronger will be the, or larger will be the amount of energy released. So lattice energy depends on charge. At the same time, lattice energy also depends on the distance of separation between cation and anion. It depends on distance of separation between cation and anions. If the separation is more, lattice energy is going to be less. Because if the separation is more, the molecules won't be closely packed. It won't be a stronger bond. Am I clear? So the amount of energy released will be less. Lattice energy is directly proportional to the charge of ions. That is, it's directly proportional to the charge of cation, directly proportional to the charge of anion, and inversely proportional to radius. Am I clear, student? Now let's have a look. Directly proportional to the charge, Z plus and Z minus, where Z plus and Z minus are the charges of cations and anions, and inversely proportional to the separation distance between cation and anion. R plus radius of cation, R minus radius of anion. Lattice energy inversely proportional to size, directly proportional to charge. Am I clear? Okay. So can you tell me, if I have to compare the lattice energy of ions like Na plus, Mg2 plus, Al3 plus, in which case I am going to get larger lattice energy, larger amount of energy released. More is the magnitude of charge, higher will be the lattice energy. If these ions form ionic compound, if they combine with anions, and if they form ionic compound, in case of this compound of Al3 plus, the amount of energy released will be much more. That lattice energy directly proportional to charge of ions, inversely proportional to radius of ions. Shall I move ahead? This lattice energy is really important. Student, this lattice energy parameter is really important. We'll be doing lot of applications where this concept of lattice energy is involved. So till then, let's move ahead and let's discuss few more concepts. Arrange the following in the correct order of lattice energy. Okay, we have to compare. We have to compare the lattice energy of Na2O, MgO, Al2O3. Just now I told you, lattice energy depends on charge. Stronger the charge, larger the magnitude of charge, higher will be the lattice energy. In case of Na2O, it's Na plus, it's Mg2 plus, Al3 plus. In which case you find stronger charge. Obviously, in case of Al3 plus, the magnitude of charge is higher. Higher the magnitude of charge, higher will be the lattice energy. So the lattice energy order will be like this: Al2O3 greater than MgO, MgO greater than Na2O. Am I clear? Next one. AlF3, Al2O3 and Aln. Cation is fixed, Al plus 3 in all case. Here it's F minus, Al plus 3, O2 minus, Al plus 3, N3 minus. More the charge of cation and anion. Lattice energy directly proportional to Z plus and Z minus. Charge of cation and anion. Charge of cation fixed. So lattice energy directly proportional to charge of anion. So can I say in case of Aln the lattice energy will be more than Al2O3, and in case of AlF3 the lattice energy will be less. Let's move ahead. Next one. LiCl, NaCl, KCl, RbCl, CsCl. Student, basically it's Li plus, Na plus, K plus, Rb plus, Cs plus. As we move down the group, the size of ions increases, lattice energy decreases. So which one will have higher lattice energy? Which one will be having higher lattice energy? LiCl, then NaCl, then KCl, then RbCl, and least in case of CsCl. Am I clear, students? Let's move ahead. Now let's try to understand the calculation of lattice energy. And student, we have developed a certain relation referred as Born-Haber cycle, and with the help of this cycle we can calculate lattice energy of any ionic compound. Let us try to understand this Born-Haber cycle. Student, let's talk about the formation of this NaCl solid. Right? How this NaCl solid is formed? It's basically formed when this Na plus gas combines with Cl minus gas. It leads to the formation of NaCl solid. The amount of energy released in this process is lattice energy. Okay. So student, now let's try to understand the calculation of this energy released. Okay. I'm having sodium solid. It's treated with chlorine gas, leading to the formation of NaCl solid. Basically, this particular equation it's nothing but thermochemical equation of enthalpy of formation of NaCl. Right? How do we represent this enthalpy of formation of any reaction? Simply write all the constituent element in their standard state. Constituent elements are sodium. Standard state is sodium solid. Constituent element is chlorine. Standard state is chlorine in the gaseous state, right? So the amount of energy released is nothing but delta HF. Okay. Now let's see how this NaCl solid is actually formed. First, this constituent element Na solid needs to get converted to, I need to convert this Na solid to Na plus gas. And for this process, we need certain energy. First, this sodium solid needs to get converted to sodium gas. And the amount of energy required in this process is sublimation energy. We provide energy, so the process is endothermic. Delta H is going to be positive. Am I clear? Sodium solid getting converted to sodium gas. The amount of energy required is sublimation energy. Now, I'm having sodium gas. I need to convert the sodium gas to Na plus gas. I need to ionize this gas. For this process, the energy which we need is ionization energy. Once again, this ionization energy also, we are providing that energy. So the process is endothermic. Delta H is positive. Na gas getting converted to Na plus gas, ionization energy. Delta H positive. So student, in order to convert this sodium solid to Na plus gas, we need two energy: sublimation energy and ionization energy. Now, let's talk about chlorine. We have chlorine there in the gas state and it's there in Cl2 form, right? First, and this Cl2 gas needs to get converted to Cl minus gas. So first I need to convert this molecular state of chlorine into its atomic state, and for that I need bond dissociation enthalpy, right? Okay, for 1 mole, let's suppose the bond dissociation enthalpy is X. I need half mole Cl2. So I need, for this reaction, right, half mole of Cl2 gas will give me Cl gas. When 1 mole of Cl2 gas is dissociating, let's suppose the bond dissociation enthalpy is X. So what will be the bond dissociation enthalpy when half mole of chlorine gas is getting converted to chlorine gas in the atomic state? X by 2, right? That's why BDE divided by 2. This calculation is really important. Okay, now I'm having chlorine in the atomic state, in the gaseous state, that is chlorine gas. Now this chlorine gas needs to get converted to Cl minus. The energy used will be electron gain enthalpy or electron affinity, and this electron affinity will be a exothermic process because chlorine is having a configuration of 3p5. As soon as it accepts one electron, it will get the configuration of argon 3p6, a much more stable configuration. So energy will be released. Delta H negative for this process. So this chlorine gas is now in their Cl minus state, Cl minus gas. Now this Na plus and Cl minus gas will combine and it will lead to the formation of NaCl solid. The energy used is lattice energy, right? Okay. So student, if I use Hess law, basically can I say delta HF is nothing but the combination of all the energy used in this process, right? Am I clear? Na solid getting converted to Na gas, in that process the energy was sublimation. Na plus gas getting converted to Na gas getting converted to Na plus gas, ionization. Cl2 getting converted to Cl gas, bond dissociation enthalpy by 2. Now the Cl gas getting converted to Cl minus gas, electron affinity or electron gain enthalpy. Now this Na plus gas and Cl minus gas combining and leading to the formation of NaCl solid, lattice energy. So delta HF is basically the combination of all these energies, right? Student, now for any compound, we'll be knowing this delta HF, we'll be knowing this sublimation energy, we'll be knowing this ionization energy, bond dissociation enthalpy. From here, I can easily calculate lattice energy. Am I clear? Let's move ahead. Student, if I talk about the conditions which favor this ionic bond formation, first, it should have high electron gain enthalpy. High electron gain enthalpy means stronger non-metallic character. It should have a strong affinity to get converted to ionic state, an anionic state, right? Okay, and high lattice energy. Obviously, if it's having a higher electronegative character, the solid will be closely packed, more amount of energy will be released, and the lattice energy will be very high, right? So if the electrostatic force of attraction is stronger, lattice energy will be much more higher. Am I clear? Okay. Low ionization energy for metal. If the ionization energy is low, obviously electropositive character will be more, and in that case ionic formation tendency to get converted to cation will be more. So low ionization energy and high electron gain enthalpy are the mandatory conditions for a stronger ionic bond formation. Am I clear, student? Student, if I talk about this bond Haber cycle, we have the different energy used: bond sublimation energy, ionization energy, bond dissociation enthalpy. All these energy, basically they are endothermic process, right? Sublimation energy, sodium solid was getting converted to Na gas. The process is endo. If I talk about ionization energy, Na gas getting converted to Na plus gas, it's exo ionization energy. Next one, bond dissociation enthalpy, half Cl2 gas getting converted to Cl gas. Here also I need to provide energy, right? This is also endo. Whereas if I talk about these two processes, electron gain enthalpy and lattice energy, in this process energy is released, right? So they are exothermic. Am I clear? So these are the released energy, whereas these are the absorbed energy. Absorbed energy should be less, released energy should be more. And now we have a question related to the calculation of lattice energy of NaCl solid. Let's do this question. I'm having heat of sublimation of sodium solid, x joule. Na solid getting converted to Na gas. The energy released is x joule, perfect. Na gas getting converted to Na plus gas. Energy released is y joule. Bond dissociation, half Cl2 gas getting converted to Cl gas. The bond energy per mole is A joule. So in this process, it will be A by 2 joule. Electron gain enthalpy, Cl gas getting converted to Cl minus gas. It is how much? B joule, perfect. And enthalpy of formation of NaCl is C joule. Enthalpy of formation is nothing but delta HF of NaCl is equals to sublimation energy of Na plus ionization energy of Na gas, right, plus BDE of half BDE of Cl2 gas, right, plus electron gain enthalpy. What's the electron gain enthalpy? Electron gain enthalpy, let's write electron affinity of Cl gas, and in the end plus lattice energy, right? Now we need to substitute the data. Enthalpy of formation C joule is equals to sublimation energy exothermic, so plus only x joule. Ionization energy endothermic, once again this one was also endothermic, ionization is also endothermic, y plus only. Bond dissociation enthalpy plus A by 2 joule, once again endothermic. All these process absorbed energy. Now electron gain enthalpy, energy is released, minus B joule. Okay, enthalpy of formation of NaCl, that we have to, that's already given, that C joule. And what's plus lattice energy, Student, even the C will also be having minus sign only, and from here I can easily calculate lattice energy. Am I clear? Shall I move ahead? Let's move ahead. Students, moving ahead, the next parameter which we are going to study, which we are going to discuss is there on the screen, and it's hydration energy, or I even say it as solvation energy. If the solvent is water, then the energy released is hydration energy. If the solvent is any other solvent, or in general we use the term solvation energy. Basically, it is the amount of energy released when 1 mole of an ionic compound is dissolved in any solvent. The amount of energy released when 1 mole of any ionic compound is dissolved in solvent, right? Okay. If the, and now student, we have two terms, hydration energy and lattice energy. Student, for an ionic compound to be soluble, this hydration energy should be greater than lattice energy. If hydration energy is less than lattice energy, compound won't be soluble. Am I clear? So if this released amount of energy is greater than the amount of energy required to break the bond, that's nothing but lattice energy, the substance is considered to be soluble. Is this clear? Let's move ahead. Okay, student, now let's try to understand the mechanism of solvation. Let's try to understand this solvation energy. Okay, I'm going to take NaCl once again. NaCl, solid, right? Okay, I'm going to provide lattice energy, or basically I'm going to break it. I'm going to break it in Na gas and Cl minus gas, right? Now this Na gas is dissolved in water. Let's try to understand this phenomenon. Water, H2O, right? H2O is basically a polar molecule, a dipole molecule, right? HOH, del negative, del positive, del positive, right? Now as soon as this Na plus is dissolved in this water, can I say this water molecule will surround this Na plus from all the sides? And can I say I will have a ion dipole interaction, Na ion in the ionic state, whereas water, it's a dipolar, lone pair, and O having del negative, dipole. So can I say we will have a ion dipole interaction? So we will have a physical bond formed between this Na plus and the water molecule, like this. Water molecule will surround Na from all the sides, through this oxygen side, because oxygen is having a del negative, del negative, del negative, del negative. This sodium Na plus will get surrounded by water molecule from all the sides, and I will have a ion dipole interaction. Because of ion dipole interaction, a physical bond is formed between the metal ions and the water molecule, right? And we know bonding is an exothermic process, right, student? So if bonding is formed, obviously energy will be released. The amount of energy released in this physical bonding between the metal ion and the water molecule is nothing but hydration energy. If it's any other solvent, then it's solvation energy. Student, one very important point. Smaller the size of ion, larger will be the extent of solvation, larger will be the hydration energy, larger will be the solvation energy. Am I clear? I hope you understood this phenomenon. Simple, as soon as any metal ion is dissolved in water, it's surrounded by solvent, it's surrounded by polar solvent from all the sides. There is a physical bond formed between the metal ion and the solvent. Since bonding is an exothermic process, energy will be released. The net summation of all the energy released is nothing but hydration energy. If the solvent is water, smaller the size of ion, larger will be the extent of solution, more will be the hydration energy released. As the size of ion increases, hydration energy will decrease because the extent of solution will be less. Okay. Le stands for lattice energy, He stands for hydration energy. Case 1, if hydration energy is greater than lattice energy, means compound is soluble. If hydration energy is less than lattice energy, compound is sparingly soluble, very less soluble, feebly soluble, or even insoluble, right? Okay. Now let's discuss the factors affecting hydration energy. Just like lattice energy, hydration energy is also dependent on charge of ions. Larger the charge of ions, higher will be the extent of solvation. If I talk about Na plus, Mg2 plus, Al3 plus, which one will be solvated to a higher extent? Al3 plus. Am I clear? Then Mg2 plus, then Na plus. Is this clear, student? Okay. So hydration energy directly proportional to charge, inversely proportional to size of ions. Just like lattice energy, hydration energy is also inversely proportional to size of ion. Larger the size of ion, smaller is the extent of solvation, smaller is the hydration energy. Am I clear? So if I have to compare the solvation of Li plus and Cs plus, which one will be solvated better? Li plus. You can see here, Li plus is surrounded by more number of water molecule as compared to Cs plus. So which one will have higher hydration energy? Li plus. Am I clear, student? As we move from Li plus to Na plus to K plus to Rb plus to Cs plus, hydration energy will be decreasing. Extent of solvation will go on decreasing. Is this clear? Okay. Hydration tendency. We have already discussed hydration tendency directly proportional to charge density. Higher the charge density, more will be the extent of solvation. Is this clear? Charge density, charge of ion upon size of ion. More is the charge density, higher will be the hydration energy. And if hydration energy is more, solubility will be more. Is this crystal clear? Let's move ahead. So you can see this is really important. Most important for JW mains. Most imp for JW mains. Upcoming JW mains. Right? As I move from Li plus to Na plus to K plus to Rb plus to Cs plus, ionic radius is increasing. Right? Size of ion is increasing. If the size of ion will increase, the extent of solvation will decrease. So hydration radii will decrease. Li, we have already seen here. You can see this is the hydration radii of Li. And this is the hydration radii of Cs plus. Which one is more solvated? The one which is more solvated will have higher radii. Hydration radii. Am I clear? This one is also asked a lot of time. Hydration radii. Hydration radii of Li plus aqueous. If someone asks you, compare the radius of Li plus aqueous and Na plus aqueous, which one will have a higher radii here? Li plus. Because if it's Li plus aqueous, I am talking about hydration radii. Is this clear? Okay. Moving ahead, the next important topic that we are going to discuss is polarization and covalent character of ionic compound. One of the most important subtopic of this particular chapter. Students, none of the ionic compound is having 100% ionic character. It definitely possesses some covalent character, and the extent of this covalent character of an ionic compound depends on polarization. And student, we use the term polarization for anion. Why? Because anions are larger in size, and whenever they approaches in the cationic field, there is distortion in the shape of anion, right? This distortion in the shape of anion is nothing but polarization. Let us try to understand. Covalent character in any ionic compound can be explained with the help of polarization. Polarization we define for anions. What is this polarization? Distortion in the electron cloud of an anion due to attraction of adjacent cation. Whenever this large sized ion will enter into the cationic field, the electron cloud, all the electron cloud present in this anion will try to move towards this cation. and because of this movement of electron cloud in one direction, there will be distortion in the shape of an ion, and this distortion in the shape of an ion is nothing but polarization. Am I clear? Let's move ahead. Now, due to this polarization, covalent character is generated because as soon as it will be polarized, now there may be some sharing of electrons between these cations and anions. They will come very close to each other, these two orbitals, right? And if they are coming close to each other, there is a chance of sharing of electron, and sharing of electron only occurs in a covalent compound. Am I clear, student? Okay. Now, this extent of polarization depends on charge density. Higher the charge density, higher will be the extent of polarization. Am I clear? Okay. Now, this charge density I define for cation. Larger the charge density of cation, stronger will be the, or larger will be the polarization of anion, and more is the polarization of anion, more will be the covalent character of ionic compound. Let's try to understand it in a simple word. Student, polarization of anion is simply dependent on magnitude of charge of cation. If I talk about Na plus, Mg2 plus, Al3 plus, which one will polarize the anion to a more extent? Al3 plus. Al3 plus is having more magnitude of charge, more positive charge, right? Larger the magnitude of charge, more will be the polarization of anion, and more will be the covalent character, right? For cation, now for cation we use the term polarizing power because cation is having a tendency to polarize anion. So for cation we use the term polarizing power, for anion we use the term polarization or polarizability. Am I clear? Now this is really important. If I talk about cation, for cation this polarizing power is used, and polarizing power of cation is directly proportional to charge of cation and inversely proportional to radius of cation. Smaller the size of cation, more will be the polarizing power. More is the polarizing power of cation, more will be the covalent character of ionic compound. Am I clear? So polarizing power is once again dependent on charge density, or even we say it as ionic potential. Charge of cation upon size of cation. More is the charge of cation, more will be the polarizing power of cation. And if the polarizing power of cation is more, means more will be the polarization of anion. And if polarization of anion is more, covalent character is more. Am I clear? Polarizing power directly proportional to ionic potential, which is directly proportional to charge upon radius. Let's move ahead. Okay. Polarizability, it is the ability of an anion to get polarized by cation, adjacent cation, right? For anion, we use the term polarizability or polarization. Okay. Factors affecting polarizability. More is the size of an ion, more will be the distortion, more will be the polarization. For cation, polarizability power is inversely proportional to size. For anion, larger the size, more will be the distortion, right? We can distort it to a larger extent, and more is the distortion, more is the polarization. So directly proportional to size of anion, directly proportional to charge of anion. Okay, let us try to understand. N3 minus, O2 minus, F minus. What do you say? Which one will be polarized to a more extent? N3 minus, then O2 minus, then F minus. Am I clear, student? Okay. It's directly proportional to size, directly proportional to charge of anion. For anion, polarization is directly proportional to charge, polarization directly proportional to size. For cation, we use the term polarizing power, directly proportional to size, inversely proportional to radius. Am I clear? Let's try to understand it now. Student, I'm having BeCl2, MgCl2, CaCl2, SrCl2, BaCl2. Anions fixed, common anion. Now we have to focus on cation. I'm having Be2 plus, Mg2 plus, Ca2 plus, Sr2 plus, Ba2 plus, right? As I move down the group, size of ion increases. With increase in the size of ions, the polarizing power will decrease. And if polarizing power will decrease, polarization of an ion will be less, covalent character will be less. So as we move from BeCl2 to BaCl2, covalent character will decrease. Polarization of anion will decrease. Why? Because size of cation is increasing as I move down the group. As we move down the group, size of cation increases. If size of cation increases, polarizing power decreases, polarization decreases, covalent character decreases. Am I clear? So which one will have maximum covalent character? BeCl2. Which one will have least covalent character? BaCl2. Let's move ahead. Effective condition of polarization, size of cation should be smaller. Size of anion should be larger. Charge on cation and anion should be high. This point is really important. These three. For more covalent character, three conditions. Small size of cation, large size of anion, and higher charge on cation and anion. Is this crystal clear, student? Shall we move ahead? Let's move ahead. We have discussed this one, right? Okay. NaCl, MgCl2, AlCl3, SiCl4. Na plus, Mg2 plus, Al3 plus, Si4 plus. Charge of cation is increasing. Polarizing power will increase. Polarization will increase. Covalent character will increase. So as I move from NaCl to SiCl4, covalent character will increase because charge on cation is increasing, right? So if the charge of cation is more, the extent of polarization of anion will be more. Is this clear? Okay, next one, AlF3, Al2O3, Aln. This one also we have discussed. Charge of anion is increasing. More is the charge of anion, more is the polarization of anion. And more is the polarization, more is the covalent character. So which one will have more covalent character? AlF3 to Al2O3 to Aln. As I move from AlF3 to Aln, the covalent character will increase. You have to compare the covalent character in the following. Cr plus 2 oxidation state. Here it's plus 3 oxidation state, plus 6 oxidation state. Charge increasing. With increase in the charge, the covalent character will increase. And with increase in covalent character, the acidic nature of oxide will increase. So which one is more acidic? CrO3. Am I clear, student? LiCl2, NaCl2, KCl2, RbCl2, CSCl. Which one will have more covalent character? LiCl. Size of this one. Anion is common, fixed. Now as I move from Li to Cs, what's happening? Size of cation increases. With increase in size of cation, polarizing power will decrease. With decrease in the polarizing power, the extent of polarization will be less. Less polarization, less covalent character. As I move from PbF2 to PbCl2 to PbBr2 to PbI2, what will happen? Cation fixed now. Anion F minus, Cl minus, Br minus, I minus. Which one will be polarized to a higher extent? I minus. Larger the size of anion, more is the polarization of anion, more is the covalent character. Am I clear, student? I hope these things are crystal clear to you all. Students, moving ahead with this polarizing power of cations, now let's discuss polarizing power of few more special type of cations. In general, we see three types of cation. A cation with pseudo-inert configuration, a cation with inert pair effect, and a cation with completely inert configuration like Na+, Mg2+, Al3+. How many electrons do they have in their outermost shell? 8 electrons. So a cation with 8 electrons in their outermost shell is referred as a cation having inert gas configuration, right? Then we have pseudo-inert configuration, a cation with 18 electrons in their outermost shell, like Cu plus, Zn2 plus, and then we have studied this inert pair effect. Cations having 18 plus ns2 electrons in their outermost shell. 18 electrons plus ns2 electrons. Because of the increased Z effective, it's tough to remove the electron from ns2, right? So a cation with inert pair effect. 18 plus 2 electrons, cation with inert pair effect. Pseudo-inert configuration having 18 electrons in their outermost shell, like Cu plus, Zn2 plus, and then we have a cation with inert gas configuration, Na plus, Mg2 plus, Al3 plus, like that, right? And if I talk about the stability, this one is the most stable, then pseudo-inert, and then inert pair effect. I hope you understood these three types of cations. Now it's time to discuss the polarizing power of these cations. Student, if I talk about the polarizing power of these cations, a cation with pseudo-inert configuration is having more polarizing power. Then we have a cation with inert pair effect, and the least one is there with cations having inert gas configuration, right? So student, if someone asks from you Zn2 plus, Zn2 plus and Na plus, which one will have more polarizing power? Zn2 plus. Which one will polarize the anion to a more extent? Zn2 plus as compared to Na plus. Zn2 plus is the cation with pseudo-inert configuration. Am I clear? Let's move ahead. So student, we have example NaCl, TlCl, CuCl, right? This is the cation Cu plus, tellurium Tl plus, and then Na plus. Na plus is the cation with inert configuration, Tl plus cation with inert pair configuration, and Cu plus cation with pseudo-inert configuration. A cation with pseudo-inert configuration is having more polarizing power. More is the polarizing power of cation, more is the polarization of anion, more will be the covalent character. So CuCl will have maximum covalent character, then TlCl, and then NaCl will have least covalent character. Is this clear? Let's move ahead. Students, now in this particular question, we have to compare the covalent character of these compounds. The compounds are LiCl, BeCl2, BeCl3, CCl4. Anion is fixed. It's Li plus, Be2 plus, B3 plus, C4 plus. More is the charge on cation, more will be the polarizing power, more is the polarization of anion, more is the covalent characters. So CCl4 will have maximum, then BCl3, then BeCl2, and LiCl will have least covalent character. So CCl4, BCl3, BeCl2, and LiCl. Third is the correct answer. Right, student? I hope you understood this particular question. Let's move ahead. Students, now let's discuss the application of Fajan's rule. And if I talk about this application, the first application that we are going to discuss is comparison of solubility of ionic compound. This is really important. Several times questions are asked on this particular application. Student, if I talk about the solubility of ionic compounds are highly soluble in polar solvents, and they are mostly soluble in polar protic solvents like water, alcohol, all these things. If I talk about polar covalent compounds, they are soluble in polar organic solvents like acetone, ether, all these things. Whereas non-polar compounds are soluble in non-polar solvent like dissolves, like. Student, now it's time to discuss the comparison of solubility of ionic compounds. Let's discuss that. Student, if I talk about the solubility of ionic compounds, it's mainly dependent on two parameters. First, lattice energy, and the second one is hydration energy. Hydration energy, it depends on both the factor. Now, which one will dominate in which case? That we have to check and that we have to decide in which ionic compound among these two parameters, which one will be a dominating parameter, that we have to decide. Student, for that I have developed a certain trick. If you follow that trick, 99.99% you won't commit any mistake. Let's try to understand that. Okay. If the common ion is smaller in size, in that case, among these two parameters, simply compare lattice energy. Simply depend on lattice energy. If the common ion is smaller in size, solubility is dependent on lattice energy. Let us try to understand that. What do we mean by this common ion? Suppose I have to compare the stability of fluorides of group 1 element. NaLiF, NaF, KF, RBF, CSF. Common ion is fluoride ion and fluoride ion is smaller in size. In this case, solubility of these compounds will depend on lattice energy. Lattice energy. Now down the group, lattice energy decreases, right? CSF will have smaller lattice energy as compared to LIF. With decrease in lattice energy, solubility increases. Lattice energy, solubility, they are inversely proportional. So which one is more soluble, LIF or CSF? Student, as we move down the group, lattice energy decreases. With decrease in lattice energy, the solubility will increase. So as I move from LIF to NAF, NAF to KF, KF to RBF, RBF to CSF, solubility will increase. Let's do one more question. Suppose I have to compare the solubility of oxides of group 1 element. I have to compare the solubility of Li2O, Na2O, K2O, Rb2O, CS2O. Oxides of group 1 element. What is the common ion? Oxide ion. Is oxide ion smaller in size? Yes. Now here solubility will depend on lattice energy. Down the group, lattice energy decreases. With decrease in lattice energy, solubility will increase. So this one is more soluble. For group 1 element oxides, as we move down the group, solubility increases. Am I clear? Similarly, hydroxides. If I have to compare the solubility of group 1 alkali metal hydroxides like LiOH, NaOH, KOH, common ion is OH minus. Down the group, lattice energy will decrease, solubility will increase. Okay, let's move ahead. If common ion is larger, if the size of anion or cation, if the Smith's common ion is larger, then solubility will depend on hydration energy. Now down the group, hydration energy will decrease, so solubility will decrease. Suppose I have to compare the solubility of carbonates of group 2 elements, right? I have to compare the solubility of BeCO3, MgCO3, CaCO3, SrCO3, right? I have to compare the solubility of these carbonates. Down the group, here now solubility will depend on hydration energy. Down the group, hydration energy will decrease. Hydration energy and solubility, they are directly proportional. With decrease in hydration energy, solubility will decrease. So as I move from BeCO3 to SrCO3, solubility will decrease. Which one is more soluble in water? BeCO3. Am I clear? I hope these things are crystal clear. Okay, let's do some questions related to this one. I have to compare the solubility of these oxides. Common ion, oxide ion, smaller in size, will depend on lattice energy. Down the group, lattice energy decreases, solubility will increase. Right? Next one. Fluoride, CSF, CSCl, CSBr, CSI. What is the common ion here? Common ion is CS plus. CS plus is larger in size. Solubility will depend on hydration energy. Now hydration energy decreases down the group, right? As we move from F minus to Cl minus to Br minus to I minus, down the group size increases, hydrogen energy decreases. And with decrease in hydrogen energy, solubility will decrease. So which one is more soluble? CSF, then CSCl, then CSBr, then CSI, right? Hydroxide, BOH whole twice, MgOH whole twice. What's the common ion? OH minus, smaller in size. Solubility will depend on lattice energy. Down the group, lattice energy decreases. Lattice energy solubility inversely proportional. Lattice energy decreases, solubility increases. Sulfate, BSO4, MgSO4, CSO4, SrSO4, BaSO4. Common ion, sulfate ion, larger. Solubility will depend on hydrogen energy. Down the group, hydrogen energy decreases. With decrease in hydrogen energy, solubility will decrease. Clear? Next one. Student, here I have to compare the solubility of these compounds. Size of cation fixed, Pb2 plus, right? Okay, this one we can do even through Fajan's rule. Down the group, as we move from PbF2 to PbCl2 to PbR2 to PbI2, can I say the covalent character will increase? With increase in the size of ion, the covalent character increases, and with increase in the covalent character, solubility will decrease in polar solvent. So which one is more soluble in polar solvent? PbF2, PbCl2, PbR2, and least soluble will be PbI2. Am I clear? Is this clear? Shall I move ahead? Let's move ahead. SnCl2 and SnCl4. This one also we can do through Fajan's rule. Sn plus 2, Sn plus 4. Larger the magnitude of charge on cation, more is the polarizing power of cation. More is the polarizing power of cation, more will be the polarization of anion, higher will be the covalent character. So between SnCl2 and SnCl4, which one will have more covalent character? SnCl4, right? And if SnCl4 is having higher covalent character, the solubility in polar solvent will be less. Am I clear, students? Let's move ahead. Now we have few exceptions in solubility. So now we are going to discuss exceptional order of solubility. Mainly two or three things. Carbonates of group 1 element, here we will have exception. Fluorides of group 2 elements and bicarbonates of group 1 elements. Let's discuss that. Student, if I talk about the fluorides of group 2 elements, BeF2. If I talk about fluoride, right? Size of ion is smaller, F minus, smaller size, solubility will depend on lattice energy, and lattice energy decreases down the group. And with decrease in lattice energy, solubility should increase. So can I say this BeF2 should be maximum soluble? But we have one exception. This BeF2 is highly soluble, right? BeF2 is highly soluble, and it's mainly because of very dominant hydration energy. The extent of hydration in Be2 plus is very high, right? And because of this exceptional hydration energy, solubility of BeF2 will be maximum. Similarly, in case of carbonates and bicarbonates of group 1 element, down the group actually the solubility should decrease, but here in case of carbonates of group 1 element, the solubility increases. Am I clear, students? I hope this parameter solubility is crystal clear to you all. Friends, moving ahead, the next parameter which we are going to discuss is the comparison of melting point, or we can say thermal stability of ionic compound. Student, if I talk about this thermal stability or melting point, thermal stability or melting point simply depends on crystal lattice energy. Stability depends directly proportional to CLE, crystal lattice energy. And if I talk about this crystal lattice energy of ionic compound, it's simply dependent on close packing. Smaller the size of cation, smaller the size of anion, better will be the packing, higher will be the lattice energy, higher will be the melting point. Am I clear? Similarly, larger the size of cation, larger the size of anion, better will be the packing, better will be the crystal lattice energy, and higher will be the thermal stability. But if cations and anions, if they don't have a comparable size, if cation is very much larger as compared to anion, in that case packing won't be that efficient, and in that case crystal lattice energy will be less, thermal stability will be less. Let's discuss about it. Smaller cation is stable with smaller anion, just now we have discussed, because packing is efficient. Larger cation is stable with larger anion, once again packing is efficient, close packing. In case of solids, close packing. Whereas if I talk about larger cation and a smaller anion, means if there is difference in size of the ions, in that case the crystal formed is relatively unstable and the compound is thermally unstable. Am I clear? Smaller cation stable with smaller anion, larger cation stable with larger anions, smaller ion is unstable with larger ion. Student, now this thermal stability depends on charge density, and thermal stability of any ionic compound is inversely proportional to charge density. What is this charge density or ionic potential? It's simply charge of ion or charge of cation upon size of cation. Am I clear? So this thermal stability inversely proportional to ionic potential, because if more is the ionic potential, more will be the covalent character, and if covalent character is predominant, obviously thermal stability of the ionic compound will be less. Am I clear? Let's move ahead. Low phi higher, low phi more thermally stable, high phi less thermally stable. Students, we have one more concept left related to the thermal stability of ionic compound, and here we are going to discuss the thermal stability of ionic compound containing monoatomic anions. Monoatomic anions, what do we mean by this term? Ions containing single atom like hydride ion, halide ions, they are monoatomic anions. And if ionic compound is formed with these anions, and if I have to compare the thermal stability of such ionic compounds, students, here thermal stability will depend on two factors. First, it will depend on lattice energy, and the second factor is electronegativity. If I am talking down the group, here you simply compare lattice energy as a dominating factor. You simply need to rely on lattice energy if you are asked to compare the thermal stability of ionic compounds containing monoatomic ions down the group. Am I clear? Down the group, lattice energy decreases, so thermal stability will decrease. Am I clear? Whereas if you are asked to compare the thermal stability across a period, then in that case the thermal stability of such ionic compounds will depend on the factor of electronegativity. Thermal stability directly proportional to electronegativity difference. Am I clear? Let's do one more questions related to this particular concept. That's it for today, students. I hope you enjoyed this particular lecture. Students, still we have to cover few important topics left in this particular chapter, chemical bonding, but we'll cover those topics in the upcoming lecture of SPDF, when we will be talking about the group chemistry. Before starting those lectures, we'll first cover these important topics like resonance, back bonding and bridge bonding. Then we'll start our discussion on group chemistry. Thank you all for watching this lecture.